Hello everyone and welcome to the Deep Learning Optimization Bootcamp. My name is Dr. Raj Dandekar. I graduated with a PhD from the Massachusetts Institute of Technology, MIT, and I completed my bachelor's BTech from IIT Madras in 2017. This bootcamp has been created and curated by myself, whom you can see over here, my twin brother, Dr. Rajat, who graduated from Purdue with a PhD, and Dr. Shridat Panat, who graduated also from MIT with a PhD. We have taught this bootcamp to so many students, so many teachers, and individual lectures are also present on our YouTube channel. However, many students and many industry professionals requested us to put this bootcamp together in one place so that at a stretch they can watch everything and learn about optimization. Why did we create this bootcamp? Well, the reason is because all of us use optimizers, whether we run a neural network or whether we are implementing a code from Kaggle or a GitHub project. There is an optimizer involved when training the deep learning framework. However, most of us do not really understand how the optimizers were developed. What's the history of the ADAM optimizer? Why does the ADAM optimizer work so well? What's the similarities and differences between gradient descent and ADAM? When should you use gradient descent? When should you use RMSProp? And when should you use ADAM? Theoretically, how do these optimizers really work from a fundamental and from a very foundational level? This bootcamp will teach you all of these things completely from scratch. So I have prepared these lecture materials and hosted on our YouTube channel separately, and they have got a great response. Now I've put all of these together into this bootcamp so that you can watch it at one go. I believe that if you watch all of these lectures together, which are collected in this bootcamp, you will be able to compare and contrast between different optimizers in a much better manner. After watching this bootcamp lecture right now, you'll be much better equipped to understand how optimizers work, why they work, and that will really help you as a machine learning engineer. Whether you are choosing an optimizer, whether you are choosing learning rates, how to avoid local minima, it will help you in training and getting better accuracies. It will also help you during inference time. So let's get started on this journey. This will be a 3 hour bootcamp, and I encourage all of you to watch this fully. Our focus through our channel and through everything we do is on in-depth understanding and in-depth learning. That's one of the main highlights of all of our videos, and this bootcamp will do just exactly that. Now, here is the table of contents which we are going to cover in this 3 hour bootcamp. We'll start with the bottom grid or the bottom level of this pyramid, which is vanilla gradient descent. Then we'll learn about momentum in gradient descent. We'll learn about ADAGrad. We'll learn about RMSProp. And then we'll see how all of these come together to form the ADAM optimizer. Each lecture will be something which you have never seen before. It will be fully hands-on, written from scratch, directly from the very basics. I'll not assume anything. I'll try to showcase everything from the very first principles. Now, before we get started, I just want to tell you a few things. To get the most from this bootcamp, which is this 3 hour bootcamp, be active on YouTube, post in the comment section what you liked, what you understood, and if you want feedback on some concepts which need to be clarified. Second thing is watch all the 3 hours of content. So watch the entire content, don't leave it halfway. And third, post your learnings on LinkedIn. So I have a lot of followers on LinkedIn. So if your comment is thoughtful, I'll post your comment on LinkedIn and I'll also highlight you who have posted this comment. Now, I want to take a bit of time to tell you all a difference between our free bootcamps like this and the paid bootcamp. So free bootcamp like this will give you detailed video content and discussion in the YouTube comments. But the paid bootcamp goes much higher than that. The paid bootcamp is live and it will involve live teaching from us, from me, Dr. Rajat and Dr. Sridat. You'll directly learn from us in live lectures. Second, you will get certificates after the course completion, which you will not get in free bootcamps like this. In paid bootcamps, you will also have assignments which will be graded. You will have a dedicated technical doubt support team from our side. And most importantly, we will also provide you guidance with and mentorship with job interview training. So the paid bootcamp is specifically geared towards people who want to make a transition in their job, who want to get a better job, uh, who want to really improve their resume, because you can put this certificate after completion on your resume. And we will also provide job interview training based on our experience getting jobs in top MLAI companies. And then we'll also invite you to our Discord community where you will get access to Discord study groups. You can form groups among students and start working on the research projects. Now, if you're interested to join these paid boot camps, we are starting all of our live boot camps and live courses in January 2025. So this is the waitlist form, and I'll be sharing the waitlist form in the YouTube information section, also in the YouTube video information section. Please fill out this form. And if you want to check out the live courses and the live bootcamp, head over to this website. I'll also attach the link to this website in the comments. So we have partnered with Sardar Patel Institute of Technology, which is one of the best engineering colleges in India. So you will get a joint certificate uh, like this from SPIT and Visual AI Labs, which you can add to your resume. And we ourselves will be your course instructors. So we'll learn from people who have graduated from MIT, Purdue, and also uh, from IIT Madras, and who have the best industrial and research experience in the world. This is probably the best live AI course which will happen in India and globally from next year. So get on this waitlist, and then we'll send you the next instructions for registration. You'll also get a coupon code to avail discount if you fill out this waitlist. Okay, now without taking any more time, let's get started with the bootcamp. And I hope you enjoy a lot in this deep learning optimization bootcamp. Thanks.
Let's say if we have a neural network such as this, which has weights, which has biases, and which has a stack of neurons and layers, we know how to find the outputs, we know how to find the loss function in the forward pass, and we also know how to find the partial derivative of the loss with respect to the weights and biases of each and every layer of the neural network. We also know how to find the partial derivative of the loss with respect to inputs of each and every layer of the neural network. And we also know how to find the partial derivative of the loss with respect to the softmax activation function or the ReLU activation function. Great. So let me introduce the problem which we are trying to solve in the first place. The problem is that we have a data set such as this, and every data set has two attributes. So on the x-axis, the attribute is x1, and on the y-axis, the attribute is x2. And each data point can belong to either of the three classes. It can belong to the red class, it can belong to the green class, or it can belong to the blue class. Our goal is that we want to design a neural network and optimize the weights and the biases of this particular neural network, so that if I give you any new point, such as let's say this point which was not there in the training data, it should correctly classify it as red. If I give this particular point, the neural network should correctly classify it as green. That's the main purpose. And up till now we have seen how to find the uh, loss in the forward pass and how to find all the gradients in the backward pass, but we have not seen how do you get to the optimum weights and how do you get to the optimum biases. So for example, if your loss function looks something like this, and you want to get here, which is the local minima, or rather you're looking at the global minima if the loss function is more complex, you want to get to this minimum point ideally. And if you start here, this is clearly not the lowest loss, right? So somehow you have to go from the starting position number 1 to the position number 2. Why we learn about optimizers is all about this journey from point number 1 to point number 2. Optimizers will help us to get to point number 2. or they will help us in this journey of going from point number 1 to point number 2. In one of our previous lectures, we have covered the importance of gradients in optimizers, right? If you start from this point, uh, it turns out that the best direction to move is the direction of the steepest descent. So ideally, we would want to move in this direction, right? So if the loss function is L, and if the parameters are W, it turns out that partial derivative or gradient of L with respect to W is the direction of steepest ascent. So it is this direction. So partial derivative or gradient gives the direction which we should move for the largest change in the function or largest change in the loss. So naturally, if we take negative of this, so negative of partial derivative of L with respect to W or negative of the gradient is the direction of the steepest descent. So negative of this gradient gives us the direction where we should move so that the loss function decreases the fastest. So this is the direction where we should be moving. And it's because of this intuition, that's why we spent so many lectures on back propagation and we spent so many lectures on calculating these derivatives, and now you will see how useful they are. Essentially, the main idea is that moving in the direction of steepest descent or moving in the direction of negative gradients is the best strategy which we can implement to minimize the loss function. So let's say you start out with random weights and you start out with random biases in every layer of the neural network. Obviously, that won't be the optimal loss, that won't be the lowest loss, and that's fine. So we will implement an iterative procedure where we will keep on updating the weights and biases. The simplest way to do this updation of the weights and biases is something called as gradient descent. And now there are many forms of this, but today we will look at the simplest version of updating weights and biases through gradient descent. We will also look at coding this in Python. So the simple idea behind gradient descent is that you start with random weights and biases and you perform iterations. In every iteration, what you do is that you move in the direction of the steepest descent. So for example, you update the weights by this formula. So weight new is the weight original minus alpha times the gradient of L with respect to W, and alpha is my learning rate. Today we will talk a lot about this learning rate parameter because when we do gradient descent is the only parameter which we can vary. Remember that although I have written partial derivative of L with respect to W, this includes all the weights of this neural network. So for example, if you look at the first layer, every neuron has two weights. So there are six weights in the first layer. In the second layer, every neuron has three weights associated with it. So there are nine weights in the second layer. So totally, if you look at this neural network, there are 15 weights which we need to update in every single iteration. The larger the neural network is, the more weights we need to update. Similarly, we do this procedure for bias also. We start with random bias values, which is typically even 0, and then we subtract the learning rate multiplied by the gradient of L with respect to the biases. Similar to the weights, each layer and each neuron will have a separate bias. So, for example, in the first layer, every neuron will have a bias associated with it. So, that's three bias terms. And in the second layer, which is also the output layer, every neuron will have a bias associated with it. So, that's again three biases. So, there are total of six bias terms and there are a total of 15 weight terms which need to be optimized for this particular neural network architecture which we have chosen. So this update rule which I have mentioned here, that needs to be applied for all the weights and for all the biases. And remember that when we need these partial derivatives, we have already found these during backpropagation. So when we instantiate a layer class in Python, we will have a forward method in that layer and we will have a backward method in that layer. What the backward method will do is that whenever the layer is called, it will automatically store the value of the partial derivative of the loss with respect to the weights, the biases, and the inputs of that layer. So all of these gradients or partial derivatives will be available to us when we do the forward and backward pass. I have spent a lot of lectures in this series on the backward pass, especially. So please have a look at it. That way, you'll appreciate this lecture much, much more. You will clearly understand why we spend so much time on back propagation. Because once you do all that hard work, now comes the easy part where you really, really can um use the knowledge which you have gained in the previous lectures. Okay, now that you all have this understanding, let me take you through the code file which we are going to implement. So today the main task for us is to implement the gradient descent optimizer in Jupyter Notebook. And the problem which we are considering is the same problem which I explained to you on the whiteboard. We have this data set and we are going to construct a neural network which basically takes in any input and classifies it into three categories: red, green, and blue. Remember that we have two activation functions here. The first layer will have the let me draw it in or write it in different color. The first layer will have the ReLU activation function, um, and since this is a classification problem, my final layer is going to have the softmax activation function. Okay, so this is the problem which we have. In the last lecture, we saw that how we defined classes in the forward pass and the backward pass. So we had a class called layer dense to create the layer. We had a class called activation ReLU, which defines the ReLU activation class after the first layer or the first set of neurons. Then we have the second layer, and then finally we have the combined softmax plus categorical cross entropy loss class at the end. Remember that since this is a classification task, the loss function which we'll be using is something called as categorical cross entropy loss. And I already have a lecture for this in this series if you are not aware of this loss. So these are the classes which we have. And now let us start looking at optimizers and gradient descent and how to implement this in Python. So we will define a separate class for the gradient descent. So this is not a stochastic gradient. So let me just change the name to GD optimizer underscore GD. But for the sake of reference, let's just keep it like this. Okay. So now when you create an instance of this class, the optimizer SGD class, it will first call this init constructor, which will take learning rate as an argument. Remember, I mentioned that for gradient descent, the only thing which you can vary or control is the learning rate. So initially, when we get started, I'm going to set the learning rate to be equal to 1. So when we create an instance of this optimizer class, the learning rate will be set to 1. And then what we will be doing is that we'll call this update params function, which will take the particular layer as an argument. So whichever layer we are considering, we'll look at the weights and biases of that layer, and then we will update the weights and biases of that layer by subtracting the learning rate multiplied by the partial derivatives of the weights and the partial derivatives with respect to the biases. You might be wondering, where do these quantities come from? So these partial derivatives actually come from the backward method, which is defined in the layer dense class. So let me actually show you the layer dense class quickly for someone who is directly coming to this lecture. So if you look at the layer dense class, it has a forward method like this, and it has a backward method. What the backward method does is that it stores the gradients of the loss with respect to the weights, the biases, and the inputs of that particular layer. So the partial derivatives with respect to the weights and biases are what we are accessing over here when we update the weights and the biases of that particular layer. So the update params method is very important in this optimizer class. Okay. Now, since this optimizer class has been defined, we can just integrate it with the rest of the code. So first we have the data set which has 100 samples and 3 classes. It's called as the spiral data set. The reason it's called spiral data set is because the data set itself looks like a spiral with 3 categories: red, green, and blue. Okay, then we will first create the initial layer So here you can see that the initial layer has two inputs, and I'm going to use 64 neurons in the initial layer. So for the sake of representation, here I only showed 3 neurons, but for the code I'm going to use 64 neurons. So I have two inputs and 64 neurons in the first layer. I'm going to chain it with an activation class, which is ReLU. Then I'm going to define the second layer, which will be having 64 inputs, which are here 64 inputs, and then finally I'll have three outputs, R, G, and B. So it will have 64 inputs and it will have three neurons, uh, which are the output values. So remember that this layer dense class, the first argument is the inputs to those particular neurons, and the second argument is the number of outputs. So in the second layer, if you see, second layer will receive 64 inputs and we will have three outputs because we'll need to classify whether it's R, G, or B. And then finally, we will chain a combined class of softmax and categorical cross entropy. In the previous lectures, we have seen why we define this combined class. Ideally, you can even define a softmax separately and the loss separately. But then in backpropagation, it gives us a tremendous advantage if we define this combined class, because calculating the derivatives just becomes that much easier. And then finally, we create an instance of the optimizer HGD class, which we have already defined over here. Okay, now what we will be doing is that we will be performing iterations. So we will be performing 10,000 iterations of the forward pass and the backward pass. And after each iteration, we'll be updating the weights and the biases of every layer according to the update rule of gradient descent. So initially, let's do the forward pass. Dense one dot forward. What this will do is that it will take the first layer and then it will calculate the output from every each of the 64 neurons. That output will be just W transpose X plus bias, where X is input and W is the weights of the first layer. Then we will apply the ReLU activation. So activation one dot forward, dense one dot output, which means that we'll take the output coming from the first layer and then we'll apply the ReLU activation. Then we'll move to the second layer. Remember, the input to the second layer is going to be the output from the previous layer. And then the output of the second layer we are going to pass to the loss activation dot forward. What this loss activation is going to do is that it will calculate the softmax output predictions, plus it will also calculate the cross entropy loss. So it will be doing two things. And then we have a code which calculates the accuracy based on whether the prediction values match the correct inputs. What's very important to note is that we have a backward pass over here. So we'll start it from the last layer. So first we'll call loss activation dot backward. Remember that the backward class or the back propagation always starts from the last layer and then we keep moving right to the first layer. So first we will do the backward pass on the loss activation, which is the combined softmax plus categorical cross entropy loss. And then what we'll be doing is then we'll be back propagating through the second layer. We'll be back propagating through the ReLU activation, and then we'll be back propagating through the first layer. Remember, when I'm saying back propagating through the second layer and first layer, whenever I call these commands, we'll be storing the partial derivative of the loss with respect to the inputs, the weights, and biases of that layer. So in this code, we are going to access the partial derivative of loss with respect to inputs. But when we come to the optimizer, we'll be accessing the partial derivative of the loss with respect to the weights and the bias. Because remember, the update params function will require the partial derivative of the loss with respect to weights and bias of the particular layer. So then finally what we'll be doing is that for both the layers, we'll be calling the optimizer.update params. So for the first layer, we'll call this, which means that it will update the weights and biases of the first layer. And then we'll call this for the second layer as well. So it will update the weights and biases of the second layer. And as the iterations are proceeding, what we'll do is that for every 100 epochs, we'll be printing the accuracy and the loss. Remember that epoch is going through the entire forward pass and entire data set once. So when we are doing 100 epochs, we'll be going through the entire data set 100 times. Remember that the data set consists of 100 samples. So this is the simple code. And if you have understood the forward pass and the backward pass, the only thing which we have added here is optimizer.update params in both the layers. So now I'm going to run this piece of code, and let us see the epochs and the accuracy in every epoch. So here you can see that the epochs have started, and I'm going to run 10,000 epochs. The accuracy is 0.33 initially, which is pretty bad, right? It's like if we are going to determine R, G, and B and classify among three classes, 0.333 is just like a coin toss. It's just predicting one third, with one third probability we are correct of our predictions. But you can see that as the epochs are increasing, the accuracy is increasing. This indicates that we are kind of moving in the correct direction, and the loss is also decreasing, which is good. This is the whole purpose of gradient descent. But as you can see, as the epochs kind of increase further and as we reach 6900, the the loss has started to stagnate. And when we reach 10,000 epochs, we'll see that the loss is 0.681. So the loss really stagnated in the last 1000 to 2000 iterations. It did not decrease too much after this. That's the first observation. In fact, even if you run this for 1 million more iterations, the loss will not decrease too much further. So you might be thinking, what happened here? Is this the best we can do? Before that, let me actually show you an animation uh, with respect to what we just saw. And so this is the spiral data set which we are considering, and we took a learning rate of 1, right? So this animation will show you what is the answer after these many number of epochs, and that answer corresponds to what we just ran in code right now. So as you can see, the optimizer is running, and here you can see the different colors, and you can see the loss and the accuracy plotted on the right hand side. Ideally, if we have done a good job, what will happen is that the red, green, and the blue. So let me again pause here. Okay, now look at this image. We have almost reached the end of this simulation, but we are nowhere close to classifying the red dots into this red color, the blue dots into this blue color, and the green dots into the green color. Ideally, if our optimizer is correct, the green background should only correspond to the green dots, the red background should only correspond to the red dots, and the blue background should only correspond to the blue dots. But now look at this data point over here. It belongs to the blue category, right? But its background is red. So it's incorrectly classified. In fact, all the points here in the top right, they are blue, but they are in the red background, which means they are incorrectly classified. This means that we have clearly not done a good job with respect to classification of the data points, which was our initial task. Look at this data point, for example. It's a green data point, but it's being classified as blue. That's also not good. If you look at the plots on the right hand side, you will see that the accuracy stagnated to around zero point 0.6 or zero point 0.7, and the loss also stagnated to around zero point 0.8 or zero point 0.7, and the learning rate was fixed as well. So this clearly shows that the gradient descent, although it's good, we decreased our loss definitely. As you can see in this plot, we decreased our loss, which is good, but we have not reached the optimum value. So now you might be thinking that, okay, what is really happening here? So it turns out that what's happening is that you are probably getting stuck in something called as a local minima. So when we look at neural network, the when we look at neural network, the loss function landscape is not as simple as what we considered over here. The loss function landscape is in many dimensions, and it can be very complex, and it can look something like this. This is just for illustration purposes. So if you look at the loss function landscape over here, you can see that it has multiple local minima. What local minima means, that it's a point which is the lowest value but in a specific region. For example, if you look at this particular point here, which I have marked here, and let me actually mark it in a different color, just so that I show it in a better way. So if you look at this particular point, this is clearly the global minima. What global minima means is that if you look at the entire loss function, this is the point at which the loss function reaches its lowest value. So this is the global minima. But at several places before the global minima, you actually have local minima, which are localized regions where that point is the minima. So if you look at this point and if you consider only this much area, this point is the lowest in that area. If you consider this point and only consider this much area, this point corresponds to the lowest loss in this area. Similarly for this point and this area. That's why these 3 points are called as local minima. Okay. Now imagine that if you start from this particular point, let's say if you start from this point and if you start with the gradient descent, and let's say if you go here, you go here, and you go here, and then you get stuck here, and then it really becomes difficult to come out of this local minima. That's why the loss function actually stagnates. That's why the loss function actually stagnates. So let me write this over here. And this is exactly what we observed, right? In the training process, the loss has clearly stagnated. So this might indicate that we have been stuck in a local minima. So the parameter which we vary, learning rate, is very important. It turns out that if we have a very high learning rate, that is also very bad, because then we'll just keep jumping around here and there, but at least we'll escape the local minima. But if we have very low learning rate, we might get stuck in a local minima. So let me show you some animations. Here is an animation of a learning rate which is too big. So let me start this from scratch. Okay, so as you can see, this is the function, and since the learning rate is very high, we just keep bouncing from one point to another, and it's very difficult to reach the global minima, which is over here. We are getting close to the global minima, as you can see, but it's a very long process, and we just keep oscillating back and forth. This is the problem with a very high learning rate. Now, if you want to look at low learning rate, there is another video which I want to show. If the learning rate is actually very low, you can look at this video. So, okay, this is a low learning rate, and as you can see, we are clearly getting stuck in this local minima over here. We are not even exploring the other side of this global minima. This is analogous to having very low ambitions. If we have very low ambitions, we always get stuck into this particular part of the loss function. We don't even know that on the other side there are even points which have lower minima. Whereas if we have very high ambitions, if the learning rate is very high, it might lead to oscillations like this. So it is very important to decide a learning rate which is kind of optimal, and sometimes that might be difficult to do, right? uh, so it turns out that there is another concept which is called momentum, and we'll come to this in the next lecture. It turns out that normal gradient descent is not too effective, and we always get either stuck in local minima or we keep bouncing here and there. That's why people introduce the concept of momentum in gradient descent. Here is how the momentum actually looks like. So let me start this video from scratch. Okay, so if you add momentum to gradient descent, here you can see that we are perfectly converging to the global minima, and then we kind of settle around here. What momentum does is that if we get stuck in local minima, it gives a small nudge, it gives a small momentum so that we are kicked out of that local minima. That's the whole idea of momentum in gradient descent. And as you can see, we have clearly reached the optimum value here. Great. In this code itself, actually, we can experiment with different learning rates, and we can see what actually happens. So let's try with a learning rate of 0.5. So now I'm going to put a learning rate of 0.5 over here, and I'm going to run this part of the code, and then I'm going to run this part of the code. Now let us look at the accuracy. As you can see, the learning rate is lower, so the iterations might take longer to reach the same level of loss which we earlier saw. But even earlier, at least we reached an accuracy of zero point 0.6 or zero point 0.7, but here we are getting stagnated to even zero point 0.5 or zero point 0.6. So this actually indicates that we have again got stuck in a local minima, and this is usually the problem with lower learning rates. Very similar to what I showed you over here, we are getting stuck in local minima probably. So if you run the animation for lower learning rates, so this is with zero point 0.5 learning rate, and if you start from scratch, you will see that the oscillations proceed something like this. Here also we try to get to the correct answer, but ultimately the optimum value which we get is a bit better, but not that great actually, because here also there are many misclassifications. For example, if you look at this particular section over here, this point the true value is red, but the background is blue, which means it's been classified as a blue point. So again, this is not very good. Here also you can see the accuracy has gotten stagnated to zero point 0.6. So this clearly indicates that just normal gradient descent is not working too much. But this gave us a lot of insight into understanding why learning rate matters, and why changing the learning rate can actually help us. Actually, increasing the learning rate can get us out of the local minima, but it can lead to many oscillations. Decreasing the learning rate too much can get us stuck in the local minima. I think that it's always better to start with a higher learning rate and see what's happening rather than getting stuck in a local minima in a lower learning rate. And the reason for this is that if you have a high learning rate, so if you have a high learning rate like this, although it's difficult to converge, all you'll at least see the different parts of the loss landscape. Like although we don't converge here, we get to this global minima multiple times in these oscillations. So we know that there is a part in the loss landscape which is actually very small. But if you start with a learning rate which is very low, you might not even discover these other parts of the loss function. So I always actually recommend to start with higher learning rates, and then if needed go to lower learning rates. Okay, this actually brings us to the end of this lecture where we discussed about optimizers, gradient descent, and implementing them in Python. We tried to do a good job, and we definitely lowered the loss with normal gradient descent. And I showed you a glimpse of momentum, and I showed you how momentum can actually help us a lot, such as, for example, this video. This is an example of momentum, and here you can see that we clearly converge to the global minimum very nicely. So in the next lectures, we'll be looking at something called as decaying learning rate, and then we'll look at momentum, ADAGrad, ADA delta, ADAM, etc., which are the modern ways to optimize or improve gradient descent a bit. So with this, I would like to say that thank you so much everyone for sticking with me in this neural network from scratch series. We have done around 20 to 21 videos now, and I think this is the series on YouTube which goes in a lot of depth in neural networks, and I don't assume anything if you have seen the previous lectures. Thank you so much everyone, and I look forward to seeing you in the next lecture. Hello everyone, welcome to this lecture in the neural networks from scratch series. Today we have a very important topic to cover. We are going to be looking at learning rate decay today, and why it is very important in neural network optimization. In the previous lecture, we looked at using a fixed step size in the gradient descent, and we saw that that eventually led to either of the two problems. If the step size was very large, we had these large number of oscillations back and forth and back and forth. But if the step size was too small, there was a high chance that we could get stuck in a local minima. I want to illustrate this with some video examples. So let me play this video here. In this video, the step size is very small. So here you can see that since the step size is small, we are getting stuck in this local minima here. We are not even exploring the entire loss landscape. In fact, at a much further point, there is an even better minima, which is much lower than the current local minima which we have found. However, because the step size is too small, we are getting stuck over here, and we are not exploring this global minima over here. In fact, there are many points on the right hand side of where we are getting stuck, where the loss is actually much lower. This is the biggest problem with a small step size. Second, if the step size is too large, then that has problems of its own. So for example, here you can see that if the step size is very large, we just keep oscillating back and forth. The advantage of this is that we do explore areas where the loss is becoming very low. So that is very good. The exploration here is very good, but we still don't land at this lowest loss because the step size is too large. So there are advantages and disadvantages with both the things. Ideally, when we are training a neural network, we should start with a high learning rate because we want to explore the entire loss landscape, right? So ideally what should happen is when we start the learning, this is what should happen. When we start the learning, I want to explore the entire landscape, and it's fine if the learning rate is too large. But then what I want to do is that as I enter further and further into next iterations, such as what is happening right now, I know that I have kind of found this area where the minima is the lowest. So there, then the step size should be very small. So this is kind of like an exploration exploitation strategy. Exploration is the initial part where the step size needs to be very large, and exploitation means that once we have kind of explored all areas of the lost landscape, then the step size should be very small so that we can converge on the global minima, which is over here. This is the main idea behind the concept of learning rate decay. So, the main idea behind learning rate decay is this exploration exploitation thing which I talked about. So, exploration means that starting when you start the training, you start out with a high step size, but then as you proceed with the training and as the number of iterations increase, you enter into exploitation mode, which is basically you start reducing the step size now so that you can reach the global minima without bouncing back and forth. So this exploration exploitation is actually written in terms of a mathematical formula in which we have two things. So we have the decay parameter, and the second thing is the iteration number. The reason why the iteration number is in the denominator is that as I increase the number of iterations, I want the step size to go on decreasing. So if you plot this as a function of time, you will see that at time equal to 0, the step size starts at alpha naught, and then it goes on actually decreasing with time. So this part here is the exploration part, and this part here as we go further down is the exploitation part. Now in the numerator we have alpha naught. So at t equal to 0, alpha equal to alpha naught. So we start with the initial step size, and then as t proceeds further, our step size goes on decreasing. So there is one more factor here which governs actually how fast our step size decreases. We don't want our step size to decrease very fast, because if the step size decreases very fast, what will happen is that the learning rate will be very small, very early. So we might get stuck in local minima. So this decay, the decay parameter or the learning rate decay, as it is called, controls how fast the step size is decreasing, and we don't want it to be very fast. So generally, for all practical purposes, the learning rate decay is kept around 0.001, which is 10 raised to minus 3. Okay, so this is the formula for the step size which we are going to be using. I just want to give you an intuition for how the step size decreases for different values of alpha naught, decay, and the time. So let's say we start out with an alpha naught equal to 1, and let's say we use the decay parameter of 0.1. So as you can see, I have shown you the values of alpha for 10 different time iterations, and you can see that alpha starts with 1.9.83, and within 10 iterations the value of alpha has actually decreased by 50%. For some problems this decay rate may work, but it's very fast. In 10 iterations we do not want alpha to decrease by half, and the reason is because the decay has been set to zero point 0.1. So the reason I showed you this numbers is for you to get an understanding of, if the decay is zero point 0.1, how fast the learning rate changes. Okay, so we are at this stage where hopefully you have understood the reasoning why we need to decay the learning rate, and now we are going to be jumping into code, and we are going to be looking at this problem which we have traditionally considered in this neural networks from scratch series. This is a classification problem. So the input data has two attributes, x1, which has been shown on the x-axis, and x2, which has been shown on y-axis. So any point which you take will have it can be represented as x1 comma x2. That's the input data. And along with the input data, every input data belongs to either of these three classes. It belongs to the red class, the green class, or the blue class. Our goal is to train a neural network which looks something like this. This is just for representation. Our goal is to train a neural network so that given any new point, the neural network should correctly classify that point as belonging to red class, the blue class, or the green class. To do this classification, we will need to optimize the weights and biases of this neural network. So, we will be doing this update procedure. In the last lecture, we looked at a simple update procedure like this, where the weights were updated and the learning rate was constant. Similarly, the bias was updated using the gradient descent rule and the learning rate was constant. Now, what I'm going to show you is that instead of this alpha, we are going to be updating the weights and the biases with the decaying learning rate. And let's compare the performance of the pure gradient descent or vanilla gradient descent with a fixed step size versus using a learning rate. So I'm going to be jumping into code right now. Great. So, we are going to be looking at the learning rate decay optimizer. In the last lecture, we defined the optimizer SGD class, where the only method was update params. What this method did was that it took layer as an argument and then it uh, updated the weights and biases in that layer according to the partial derivatives of the loss with respect to the weights and biases which were returned by that layer. Remember, whenever a layer class is created, it has a forward method and a backward method. So we have stored the partial derivative of loss with respect to the weights and biases of that layer through the backward method. We are just accessing those partial derivatives through layer.d weights and layer.d biases, and then we perform the update rule. When we look at the learning rate decay, we will be introducing one more parameter here. So in the without the learning rate decay, when the optimizer was initialized, we just had the learning rate as the parameter, but now there is also the decay parameter whose by default value is set to 0. And then one more thing which we'll be doing is that in this init constructor, we'll be tracking two things. We'll be tracking the current learning rate and we will also be tracking the iterations, because the learning rate depends on both these things. It depends on the current learning rate and the iterations. We'll be tracking the uh, initial learning rate as well. Okay. So now what we will be doing is that before any parameter is updated, we will call this function once, which is pre-update params. So that will set the current learning rate to this formula over here. And then what we will be doing is that we will be updating the weights and the biases. So this update params was there in the previous class also, where the learning rate decay was not used. In this method, what we do is that we just use the current learning rate and then update the weights and the biases accordingly. And note that the current learning rate is set by this formula. So this is alpha divided by 1 plus decay into t iterations. This is exactly the formula which we had seen here. The initial alpha divided by 1 plus decay into t. And then what we are doing here is that after the parameter actually updates, we are increasing the number of iterations by 1. So then the iterations will change every time, and then through that the current learning rate will be changing at every single iteration. So as the iterations proceed, we will be changing the learning rate through this pre-update params function, and then with the current learning rate we'll be updating the weights and the biases, and then we'll be of course increasing the iteration count after every iteration has been done. So this is the new optimizer class which we have, which includes the decay rate. And then the forward pass and the backward pass remain similar to what we had seen earlier. So in the forward pass, what we do is first we define the spiral data, which has 100 samples and 3 classes. Um, so this is the spiral data which we have introduced over here. This is the spiral data. We have 100 data points and we have 3 classes: red, green, or blue. We define the first layer which has 2 inputs and 64 hidden units. That is chained to the ReLU activation. Then we define the second layer which has 64 input units and 3 outputs. So these are the final output values which are then passed through the softmax activation and the categorical cross entropy loss. So this is the forward pass, or rather we are creating the instance of the class here, and then we'll be calling the forward method on all of these classes. uh, Before calling the forward and the backward method, first we will be defining the optimizer, and here we are going to be setting the decay rate to 0.001. Remember, this decay rate is generally good because we don't want a much larger decay rate. That would make the learning rate too small initially, and we might get stuck in a local minima. So we are going to be running 10,000 iterations. First, I'm going to be running the forward pass through the first layer. I'll chain it to the ReLU activation. The output of the ReLU activation will be going to the second layer, and then I'll calculate the softmax output and the cross entropy loss. In this portion of the code, we are just printing out the accuracy, the loss, and the current learning rate at every epoch. Remember, one epoch means going through the entire data set once. And then we are of course going to be doing the backward pass because we need to update the weights and the biases of the layer. So we are going to call the loss activation backwards. We'll start from the backwards. So first we'll find the partial derivative of loss with respect to the softmax inputs. Then we'll go backwards, find the partial derivative of loss with respect to the weights and biases of the second layer. Then we'll find the partial derivative of loss with respect to the ReLU input, and then we'll find the partial derivative of the loss with respect to the weights and biases of the first layer. Once that is done, we call the optimizer.pre-update params, and then we will update the parameter values based on the current learning rate and based on the partial derivatives which have been computed over here. And then we call this optimizer.post-update params because remember, we need to increase the iteration count every single time because that's used in the calculation of the current learning rate. So now this entire code has been defined. So now I'm just going to run this piece of code right now, and we are going to be tracking the accuracy. So here let us look at the accuracy. So the epochs are increasing right now, and we can see that the accuracy is increasing to zero point 0.5, which is very good. And we are right now at 3000 epochs. The loss is decreasing slowly, which means that we are not getting stuck in a local minima. As you can clearly see, the loss is still continuing to decrease. Um, Even as we reach 6600 epochs, the loss values are decreasing, the accuracy values are increasing. In fact, the loss has almost become, it has become less than zero point 0.7 now. And we are still keeping on going down. So after 10,000 iteration, I get an accuracy value of 0.717 and I get a loss value of 0.653. Let's compare it with the accuracy value from without using the decay rate. So remember, currently with the decay rate, we got an accuracy of 0.717. And in without using the decay rate, after 10,000 epochs, the accuracy was 0.573. And here we are clearly getting stuck in a local minima because the loss is not continuously decreasing, as you can see. Uh, and the loss in the previous case was 0.768. But in this case, when we use the learning rate decay, the lowest value of the loss towards the end was 0.653. And here you can see how smoothly the loss has decreased, which is another indication that we don't have oscillations and neither we are getting stuck in a local minima. On the rightmost side, you can see that I've printed the learning rate. The learning rate starts out from 1, and as the learning rate decays, or as we move further and further into the iterations, the learning rate has now become zero point 0.1 at the end of 10,000 iterations. That's the advantage of using a learning rate decay. I want to show you this in terms of visual videos. So let us have a look. First, let us have a look at without using the learning rate decay. So here we can see that learning rate decay has not been used, and on the right hand side we can see that the loss and the accuracy values are being plotted. We can see that as we reach towards the end, the accuracy is going to around 0.55 or zero point 0.6, and the loss is stagnating. The performance on the data does not seem to be quite good because all of these points here, the prediction says that they should be in the red category, but the data actually shows that there are blue points and green points also here. So we are making a lot of mistakes. Even if you see here, actually, if you see in this part, the prediction says that there is all a green boundary, but there are red points also here, which means that all of these points are getting misclassified. Now let us look at the video with decay introduced. Okay, so I'm playing this video here right now, and here we can see that we have a decay rate of 1 into 10 raised to minus 3. And as the video is we can see that the accuracy is increasing to much higher value than it was before, and the loss is also decreasing very smoothly. So as we reach towards the end of this video, we can see that we are doing slightly better in terms of the comparison, because here, if you look at this top right region, and if you compare it to, so in the previous plot the top right region was all red, so all these points were misclassified. But in this plot the top right region has good segregation. So for example, here it's blue, and that's because these blue points need to be correctly classified. And then there is transition to a red background here because there are red points over here. Then there is again transition to blue background. So this actually seems to be doing a much better job at classifying the data than if we did not have a learning rate. So this is the real advantage. This is the real advantage of using a decaying learning rate, as what we have seen in today's lecture. What a decaying learning rate actually helps us to do is that it helps us prevent local minima, and it actually also helps us prevent uh, later oscillating with large step sizes. So it kind of solves the problem of having too low a step size and too high a step size. So we start the training process with a higher step size, so we can explore the entire loss landscape, and then we start reducing the step size as we are getting closer and closer to finding the global minima. This does not guarantee that we will always find the global minima, but as I just demonstrated to you, it is better. In many cases, it is better than just having a fixed step size. However, it turns out that this is not the best. There is one more method which is much better than this, and that is actually gradient descent with momentum. We'll be exploring this in the next lecture. Thank you so much, everyone, for listening to this lecture. I hope you learnt a lot. We will see you in the next lecture. Hello, everyone. Welcome to this lecture in the Neural Networks from Scratch series. Today, we are going to be looking at gradient descent with momentum. In the previous lectures, we have looked at normal gradient descent with a fixed step size, normal gradient descent with a step size decay. But today, we are going to introduce a new term which is called as momentum. And we are going to be discussing why momentum is important and why it is used to accelerate gradient descent uh, convergence and also reduce the number of oscillations in gradient descent. All the modern neural network frameworks use one version of momentum which is called as ADAM. So this concept forms the basis of the way gradient descent is used in all modern machine learning problems. So let's get started with understanding the concept of gradient descent with momentum and why it is needed. In the first case, so this I'm going to call as case 1. Let us assume that momentum is not there and step size is a bit large. What will happen in this case is that, um, initially, let's say we start from this point here which I have marked, and we want to go to this minima. What will happen because of this large step size is that first we will move in this direction, then the gradient will point in this direction, then we'll move in this direction, then we'll move in this direction. Remember, we always go in the direction of negative of the gradient. So the negative of the gradient lies in these directions, right? Because for example, if I'm at this point, the gradient kind of lies in this, the negative gradient lies in this direction, etc. So that's why I'll keep oscillating back and forth and back and forth and back and forth. This will lead to a huge number of oscillations before I reach the minima. So reaching the minima will be delayed. Other way to say this is that it will take a long amount of time and iterations for us to reach the minima if we use a normal gradient descent in this case. Ideally, what we would want is that if we start from a point like this, instead of bouncing back and forth, we want to have this kind of a straight line, smooth path towards the minima. That is what we ideally want. What momentum does is that if we add momentum towards the gradient descent, it helps us reduce the oscillation, and that's why we can get a smoother path like this. And that's the reason why the time to reach the minima decreases and the gradient descent convergence becomes much faster. The reason why momentum really helps is that, and this will also help to explain the concept of momentum. The way I like to think about momentum is that the past matters. So if you look at normal gradient descent, if we are at this point, we just look at the gradient at this point, right? The negative of the gradient, which might be in this direction shown by the arrow. So we move in that direction. But what about the directions which we have learnt in the past? Before even coming to this point, we have calculated the gradients at several points, such as this point, etc. What would happen if we include all the past gradient updates to calculate the current gradient direction update? The way it will work in this particular case is that, let's say if we look at this point, and let's say if we look at the past gradient updates. So before finding the gradient at this point, we found the gradient at this point and at this point, right? So the first direction of the gradient was like this, which is shown by this arrow here, and the second direction of gradient was like this, which is shown by this arrow here, right? Now what will happen if we add these two directions? If we add these two, if we add this direction to this direction, what will happen? Let's first decompose it into a vector. So this direction can be written as left vector and a down vector, and this direction can be written as a right vector and a down vector. So if we add these two vectors, what will happen is that the left and the right will cancel each other out, and the only thing which will survive is the downward direction. Do you see what is happening here? The moment we take past gradients into account, the oscillations in the left and right side reduce because they cancel each other out. So the only component which actually survives is in the downward direction. And if we give a lot of weightage to the past when you compute the gradient at this point, it will kind of imply that there is a sense that we should generally move in the downward direction. So there is a higher probability that we will get nudged towards the downward direction at all the time points, and so we will converge to the minima in a much smoother manner. This is what is happening behind the scenes. What momentum is actually doing is that momentum uses the previous update direction to influence the next update. So the past really matters, and the past teaches us a lot. For example, in this case, the past teaches us that the left and the right should cancel each other out. So the only direction which will survive is this downward bottom direction. So we will move in a much smoother manner towards the local minima in mostly a vertical direction. There is a very nice animation which I would like to show over here. If you look at, if we don't include momentum at all, so look at this slider here where the momentum is zero. I want you to look at these oscillations. We can see a large number of oscillations here, right? Now let me start increasing the momentum value slowly and look at the oscillations. As I increase the momentum value, do you see what's happening? The solution is converging more quickly towards the optimum. That's the number one observation. And the second observation is that the oscillations are decreasing a lot. Let me play this again. So now the momentum is zero and the solution is over here. If we go on increasing the momentum, what will happen is that the oscillations will reduce and the solution is reaching much faster towards the optimum. That is the main concept behind momentum. It reduces the oscillations which gradient descent can produce by taking into account the past update direction or the previous update direction in order to influence the next update. And because we use the previous update direction to influence the next update, the number of oscillations go on reducing. And that's why we converge in a much faster manner towards the minima. If you understand this concept visually, now let us look at how momentum is represented mathematically, right? So, in a normal weight update, what we typically do is that we take the current weight, or we say that the new update is the old update minus alpha times the partial derivative of the loss with respect to the current weight. That's it, right? But in momentum, we'll be doing a new thing. When we include momentum, the weight update is given by a new formula. When we consider the weight update, what we are going to do is that we are, of course, going to use this term which is negative of alpha times partial derivative of loss with respect to weight. That will stay the same, like what it was without momentum. But we are going to add one more term here. So let me highlight this term in green. This term is the momentum factor. So this is a fixed value. This is a fixed value multiplied by the previous weight updates. That's it. So we are going to define the weight update as a summation of two terms. The current gradient, which is this minus alpha times partial derivative of L with respect to W, but we are going to take into account the effect of the past. And the effect of the past is given by the momentum factor, which is the fixed value, into the previous weight updates. This previous weight updates consists of the entire history of the past, because the previous weight update will depend on the value prior to that. So it will all accumulate when we come to the current weight update. And to determine how much the past matters, that is actually determined by the momentum factor. If the momentum factor is very low, it's almost zero, it means that the past does not matter too much, and we just need to update the weight by minus alpha times partial derivative of L with respect to W, which is normal gradient descent. If the momentum factor is high, so if for example the momentum factor is around zero point 0.9, which is how much it is typically used in practice, it means that the past is given a lot of importance, and it will carry a lot of weightage when we decide the current weight update. The way it is written in terms of mathematics is that the new weight is given by the old weight plus the weight update. So Wt, which is the weights at time t, is given by the weights at time t minus 1 minus alpha times partial derivative of L with respect to W, which is the current gradient, plus the momentum factor into previous weight updates. So this is the direction of the previous changes. Try to understand these terms intuitively so that you don't forget it. In momentum, the way we update the weight is that we first add a negative of the alpha times partial derivative of L with respect to W, which is the current gradient. Until this part, it's normal gradient descent. But then we add a term which corresponds to the direction of the previous changes. So this is the momentum factor multiplied by the previous weight updates. So this is how I'll be updating the weights when I'm going to include the momentum. And when I say alpha, I'm not going to use a fixed step size here. I'm going to use a decay rate. So in the previous lecture, we have looked at the learning rate decay, which is basically decreasing as the number of iterations increase. So the learning rate actually decreases with number of iterations like this. So when we use momentum, there are actually three parameters which we have. There is alpha naught, which is the initial step size. There is the decay parameter, and there is also the momentum factor here, which governs how much the past actually matters. I hope you have understood up till now. because now we are going to be jumping into the momentum code, and we are going to be applying on the problem which we have traditionally considered in this series. The problem is that of a classification problem. We have a data set, and each data set has two attributes, x1 and x2, and every data set belongs to either of the three classes, red, green, or blue. The task which we have is that we want to design a neural network and optimize the weights and biases of this neural network, so that whenever you are given any new point, such as let's say you are given this point, you will classify it correctly as blue. If you are given this point, you will classify it correctly as red, etc. So the whole discussion about momentum, learning rate, decay is for the update rule of the weights and biases. So the way we are going to update weights and biases in each iteration in the momentum is using this formula. If you have this intuition in mind, understanding the code will become much easier. So now I'm going to be jumping into the Python code. And before we do the forward and the backward class, first I want to define the class for the optimizer. And here I am going to first have an init method which will be called by default. And I have three parameters here. As I mentioned, we have the learning rate, we have the decay, and we have the momentum. By default, the learning rate is set to 1, and the decay is set to 0, and the momentum factor is set to 0. Have a look at what all we are tracking here. We are tracking the iterations, we are tracking the decay value, and we are tracking the current learning rate and also the uh, momentum parameter. So the momentum parameter is being tracked, the decay parameter is being tracked. More importantly, the current learning rate also is being tracked. Remember, the learning rate is not fixed and we are going to vary it with the iterations. The way the learning rate is being varied is that before any new iteration is going to start, we are going to update the learning rate by this formula. This formula is an exact representation of what we have seen over here. So the learning rate is alpha naught, which is the initial step size, divided by 1 plus decay into time. This is exactly what is written here. The current learning rate is alpha naught divided by 1 plus decay into the current iteration. This is the most important part in the momentum code. What we are going to do is that if the momentum parameter is not 0, if it's 0, then we are not using momentum. So then we don't go into this part of the code, and we will just do the vanilla gradient descent. And remember, in vanilla gradient descent, the weight updates are just negative of alpha into the derivative of the loss with respect to weights and the biases. But when if we are going to be using momentum, we are going to be defining two things for every layer, two attributes for every layer. One is called as weight momentums, and second is called as bias momentums. Essentially, the weight momentum and the bias momentum will be the weight updates at the current iteration. So when I said that in the momentum we are going to be we are going to be using previous weight updates, these previous weight updates are stored in this object called layer dot weight momentums, and the previous bias updates are stored in this object called layer dot bias momentums. So as we saw here, the weight updates will be the momentum factor into previous weight updates minus alpha times partial derivative of loss with respect to the weight. So the weight update will be the momentum factor multiplied by the layer dot weight momentums, which is the previous weight update, minus alpha times the partial derivative of loss with respect to weights. And this is that part where we set the layer dot weight momentum to the previous weight updates. Very similarly, for the bias updates is the momentum factor multiplied by the previous bias update minus alpha times partial derivative of loss with respect to the bias. And then we store the bias momentum object with the previous bias updates. That's it. So if we actually don't use momentum, as I mentioned before, we'll be using weight updates at just minus alpha times partial derivative of loss with respect to weights, and bias updates as minus alpha times partial derivative of loss with respect to the biases. And then the weights in each layer will just be weights plus the weight updates. So if we don't have momentum, The weights will be just weights minus alpha times partial derivative of loss with respect to weights. But if we do have momentum, then the new weights will be weights minus alpha times partial derivative of loss with respect to the weight plus momentum factor into previous updates. So then after this class has been defined, this optimizer class, we will update the weights and biases and store the new weights and biases in that layer. Remember that we have to update the iteration every single time, because our current learning rate depends on the current number of iteration. So our learning rate is going to start from a high value and then it is going to be decreasing, since we are using a decaying learning rate. So this is the optimizer class for the momentum. And now we are just going to be implementing the forward pass and the backward pass. So we have a spiral data. This data I already showed you over here. Let me again show you. This is a spiral data which we have. We are going to be using 100 sample data points, and each data point can belong to either of these three classes: red, green, or blue. Initially, I'll define the first layer which has two inputs and 64 units. I'll chain it with a ReLU activation. Then I'll define the second layer which has 64 inputs and 3 outputs. These 3 outputs will then be passed through a softmax and a categorical cross entropy loss. I'm going to be defining the optimizer here. Remember that if I don't pass in anything, by default decay will be set to 0 and momentum will be set to 0. But I'm going to be using the decay value as 1 into 10 raised to minus 3, and I'm going to start with a momentum value of zero point 0.5. And now I'm going to be running the uh, forward pass and the backward pass for 10,000 different iterations. So let me show you how these iterations actually proceed. First, through the first layer, I'm going to do a forward pass. The output of the first layer is an input to ReLU. The output of the ReLU is an input to the second layer. And the output of the second layer will determine my softmax and my final loss. This part of the code is just used to calculate the accuracy, and at each epoch, I'm going to be printing the accuracy, loss, and the current learning rate. Remember, one epoch is going through the entire data set of 100 samples once. And then, of course, we are going to be doing the backward pass. So, first, we'll start from the end. We'll start from the finding the partial derivative of loss with respect to the softmax inputs. Then we'll find the partial derivative of the loss with respect to the weights, biases, and inputs of the second layer. Then we'll find the partial derivative of loss with respect to ReLU input. Then we'll find the partial derivative of loss with respect to weights, biases, and inputs of the first layer. Based on these partial derivatives, we are going to be updating the weights and the biases of every layer. And these pre-update params, update params, and post-update params functions have already been defined in the optimizer class. So this is the pre-update params, this is the update params, and this is the post-update params. So this is the forward and the backward pass. So I'm going to run this piece of the code now, and let us try to have a look at the epoch, the accuracy, and the loss value. So as you can see, the accuracy has started to increase and the loss is steadily decreasing, which is a good sign that we are not getting stuck in a local minima, which is one feature of momentum. It avoids getting stuck in local minima and then really improves the gradient descent convergence. As you can see, we have obtained an accuracy of 0.83 and a loss of 0.465. If you have watched the previous lectures, you will see that this is the highest accuracy. So keep this accuracy in mind, 0.83, and let us look at the accuracy first in the learning rate decay. So when we use the learning rate decay, the accuracy was 0.717, which is much lower than the current accuracy. So this accuracy of 0.1717 is learning rate decay, but without momentum. So with momentum, the accuracy increased from 0.717 to 0.83. And if you look at even without learning rate decay and without momentum, the accuracy is even bad. The accuracy is 0.573. So when we incorporated learning rate decay, the accuracy jumped from zero point 0.7 to the accuracy jumped from 0.57 to zero point 0.7. And further, when we included momentum, the accuracy jumped from zero point 0.7 to 0.83. Amazing. This is the highest accuracy which we have obtained so far. But I believe let's try to increase the accuracy even further by using a momentum factor of zero point 0.9. So remember, if the momentum factor is zero point 0.9, it means that we are giving a much higher weightage to the past. So I'm going to run this piece of the code now. So now let us keep a track of the accuracy. As you can see clearly, the accuracy has already reached the value of zero point 0.9, which is amazing, which means that the past really matters, and giving so much weightage to the past has led to an accuracy of very, very high values. So here you can see that I have now started to converge with respect to the accuracy and the loss, but it's the best accuracy and loss which I have obtained so far. At 10,000 epochs, the accuracy is 0.953 and the loss is 0.128. So here you can clearly see why using a high momentum value helps. Secondly, you must have seen the importance of using momentum in the first place. If momentum is not used, then we saw that the accuracy was zero point 0.5 or zero point 0.7. It's pretty low. But ever since we started using momentum, the accuracy has reached to zero point 0.9 and even more than zero point 0.9. This clearly demonstrates the advantages of using momentum. I want to now show you some videos which can further demonstrate this concept. So first, let us see this video which uses a learning rate of 1, but it does not use any learning rate decay, or it does not use momentum. As you can see, this is almost the final prediction which we get, and it's pretty bad because if you look at this region here, it's blue, but there are green points also which are misclassified. If you look at this region here, it's a green region, right? But there are red points also here which are misclassified. So this is pretty bad. Second, if we use a learning rate decay, then let's see what we get. If we use a learning rate decay, then things become slightly better, but things are not that great also. So if we use a learning rate decay, this is the maximum performance which we can get, and this is better, right? But it's still not quite amazing, because let's look at these two green points here. This is ideally a blue region, but there are green points also here, so they are misclassified. There is one green point here which is misclassified as red. It is a definitely better than uh, the without learning rate, but this definitely does not look like a spiral, right? I want my prediction colors to be looking like a spiral, which is my true data set. Now let's look at the momentum videos. So this is a momentum video, and I have now run the different iterations for a momentum of zero point 0.5, which was not the best one, but let's see how it is doing. First of all, we can see that I have slightly started to see spirals now. I am definitely started to see spirals now. Here you can see the green boundary almost looks like a spiral, the red boundary almost looks like a spiral, and the blue boundary almost looks like a spiral. So this is amazing, but still you will see that there are few misclassifications even in this example. So then we will go with momentum value of zero point 0.9, and then let's see what we actually obtain. So now you can see that the momentum value is zero point 0.9, and then we have obtained perfect spirals. Look at the red boundary. It looks like a spiral which is perfectly capturing the red data. Look at the blue boundary. It looks like a spiral which is perfectly capturing the blue data. And look at the green boundary. It looks like a spiral which is perfectly capturing the green data. So as you can see, when we use momentum, we are obtaining brilliant results here. In fact, the neural network has given us very high accuracy and very low loss values. In the next lecture, we are going to be looking at even further advancements on this momentum concept, which are called as ADAGrad, ADA delta. And finally, we'll also be looking at the ADAM optimizer. So, in this lecture, I want you to remember these takeaways: that when you use gradient descent with momentum, it reduces oscillations and it really helps convergence. And we demonstrated that on a real life practical data set, which is a spiral data set. Uh, this is much better than not using momentum. So, having a learning rate decay definitely improves, but having momentum really, really improves the neural network optimization. In the next lecture, as I mentioned, we'll further develop on the momentum concept and finally try to explain the ADAGrad and the ADAM optimizers, which are very routinely used in practice. Thank you so much, everyone. I'm trying to make these lectures as intuitive and visual as possible so that you definitely go through the code, but you also understand the intuition behind why we are running the code. That's why I'm showing you this whiteboard approach code as well as video files. Thank you so much, everyone, and I look forward to seeing you in the next lecture. Hello, everyone. Welcome to this lecture in the Neural Networks from Scratch series. Today, we are going to learn about an important optimizer for neural network training, and that optimizer is called as ADAGrad. Eventually, ADAGrad led to the development of the optimizer ADAM, which is now used commonly in most modern machine learning frameworks. So, to really understand the ADAM optimizer, first we need to understand the basics of the ADAGrad optimizer. In many modern machine learning settings, ADAGrad is not used nowadays, but still the concepts which ADAGrad teaches us are very important, and that's why it's necessary to learn about this optimizer. In the previous lectures, we have looked at gradient descent with momentum, and we saw that when we use momentum, we really get an accelerated convergence, which means that we reach towards our minima in a much faster way with very less number of oscillations. So, momentum actually helps us to reduce the oscillations. And we saw that with momentum, the accuracy of the neural network training is very high and the loss is very low. Essentially, the way momentum worked is that it also gave importance to the previous weights. But the key thing to note in the momentum, if you look at the weight updates, of course, the weight updates depend on the previous weight updates. But if you look at the learning rate alpha, this is a common shared learning rate among all the weights. So, all the weights of the neural network use this same alpha, and that alpha decays with time. So we specify a learning rate decay, and as the iterations go on proceeding, alpha goes on decreasing with time. This is to make sure that we start off with a high step size and we explore the entire loss landscape, but later the step size goes on reducing so that when we settle in places close to the global minima, we don't keep on oscillating. The key thing which I want you to note is that in momentum, there is a common or a shared step size among all the weights. Although it is decaying with time, it is the same step size which all the weights use. This is the key idea upon which ADAGrad operates. The main premise or the main concept of ADAGrad is that okay, why do all the weights essentially have the same learning rate? Why is there a common learning rate across all the weights? Why can't the different parameters or the different weights of a neural network have different learning rates? And this is a very key concept to understand. So, the first thing which we will look at is that how does it help us if different weights have different learning rates associated with them? Let's look at a neural network like this. This is a neural network which has two inputs over here. It has three neurons in the first layer and it has three neurons in the output layer, which are then used to calculate the loss. In the first layer, every neuron has two weights associated with it. So there will be six weights in the first layer. In the second layer, every neuron has three weights associated with it, and there are three neurons. So there will be nine weights in the second layer. In the first layer, there are three neurons, so there will be three biases, one corresponding to each neuron. And in the second layer, there are again three neurons, so there will be three biases, one corresponding to each neuron. So essentially, there are 6 plus 3 plus 9 plus 3, which is 21 different parameters here. And ADAGrad says that all these parameters should have different learning rates for better performance. Let's see why do we need different learning rates for different weight parameters. So I am going to take a simple example here, which is something like, so let's say if we have just two parameters w1 and w2, and the loss function is a function of w1 and w2 given by this formula: w1 square by 100 plus w2 square is the loss. Okay, if you plot this in a two dimensional landscape, the contours of the loss will look something like this. Since there is a factor of 100, we have the loss function which is hugely stretched in the horizontal direction, but which is not very stretched in the vertical direction. So w1 is my x-axis and w2 is my y-axis. So let us do some calculations. Let us take w1 equal to 1 and w2 equal to 1. It will probably lie somewhere around here, 1 comma 1, right? And I want to find the partial derivative of loss with respect to w1, and I want to find the partial derivative of the loss with respect to w2. So let's find the partial derivative of loss with w1. When we do this, w2 will be treated as a constant. So we'll just take the derivative of this term with w1, which is 2w1 divided by 100. And since w1 is equal to 1, the partial derivative of loss with respect to w1 is 0.02. Now let us find the partial derivative of loss with respect to w2. When we do this, the first term has w1, so it will be treated as a constant. So all we need to do is find the derivative of this term with w2, and that is just 2w2. Since w2 is equal to 1, the partial derivative of loss with respect to w2 will be equal to 2. Now I want you to compare these two partial derivatives. Partial derivative of loss with respect to w1, which is 0.02, and partial derivative of loss with respect to w2, which is 2. So you will see that partial derivative of loss with respect to w2 is 100 times greater than the partial derivative of the loss with respect to w1. What does this mean? It means that if we make small changes in w1, it would not increase or decrease the loss too much. But if we make small changes in w2, that will be 100 times more significant than changes in w1. What does this tell you? Let's say if we are doing the gradient descent and we are updating w1 and w2. So let's say we are using the same step size to update w1 and w2, then both w1 and w2 will be updated by alpha times. So w1 will be updated by alpha times partial derivative of L with respect to w1, and w2 will be updated by alpha times partial derivative of let me write this again, partial derivative of L with respect to w2. So w2 will be updated by this value. Now since partial derivative with respect to w2 is so high, you will see that w2 will change by a huge amount. But if and partial derivative of L with respect to w1 is very low, so w1 will not be changing too much at all. This would indicate that some weights will change very fast and some weights will change in a very slow manner, and this is not very good at all. In fact, this can lead to uh, non-convergence of the loss, because one weight value will not update at all. Ideally we want normalization, which means that all the weights are updating on the same scales. We do not want one weight to be updating very very quickly, and we do not want the other weights to be not updating at all. If some weights are not updating, it means that that neuron is not contributing anything. It's like a dead neuron. Since we want all the neurons to be contributing, ideally what we want is that if partial derivative of L with respect to w2 is so high, then why don't we make the alpha associated with it? So let me mark it with a different color. If the partial derivative of L with respect to w2 is so high, why don't we make the step size or alpha associated with it to be very low, so that the change is same? This can also be represented as, if the partial derivative of L with respect to w1 is so low, why don't we make the step size associated with it high? So let me call this alpha 2 and let me call this alpha 1. So ideally what we want is that we want alpha 2 to be much, much smaller than alpha 1. So ideally we want alpha 2 to be much, much smaller than alpha 1, because the partial derivative of L with respect to W2 is much, much higher than the partial derivative of L with respect to W1. So to put it in another words, the step size for W2 should be smaller than the step size for W1. This can also be described as follows: higher the parameter derivatives, smaller should be the step size. So if the parameter derivative is very high, the step size should be small, and if the parameter derivatives are small, then the step size should be large. This is what we ideally want, and that's where the concept of ADAGrad comes into the picture. What ADAGrad says is that we don't want one weight to be updated much faster than the other weights. That would lead to some neurons being inactive or dead neurons. We want all neurons to be contributing. So the step sizes should be in accordance with the parameter derivatives. If the parameter derivatives are high, the step sizes should be small. If the parameter derivatives are small, the step sizes should be large. I hope you have understood the intuition behind ADAGrad. Now I'll move to the second part of this lecture, which is the mathematical procedure for ADAGrad. And in the third part, we will look at how to code ADAGrad in Python. So, okay, we know intuitively what we want to implement. We want the step size to be inversely proportional to the parameter derivative. Higher the parameter derivative, smaller the step size. Smaller the parameter derivative, larger the step size. That's what we want. So the way ADAGrad is implemented in practice is as follows. First, for every given parameter, we maintain an history of the previous gradients of that parameter. Note that as the iterations are proceeding, the gradients of the loss with respect to a parameter go on continuously changing, right? So there is a history of these gradients. So we maintain this history in this variable which is called cache or cache value. So what this cache will do is that, let's say we start out with the iterations, the cache will be set to 0. In the next iteration, the cache will be set to the gradient of the parameter whole square. And in the next iteration, the cache will be the previous cache value plus the current parameter gradient the whole square. So basically, to find the cache value at a given time point, you add the parameter gradients of all the previous iterations with the current iteration. That's how you find the cache value. So the main thing to note here is that we are storing a history of gradients, and we are not just storing the gradient value, but we are storing the value of gradient square. And I will tell you why we are doing gradient square in a minute. But for now, just keep in mind that we are storing the history of the parameter gradient values or the partial derivative of the loss with respect to that parameter. So let's say we are in the fifth iteration. We will find the partial derivative of the loss with respect to weights in the current iterations, square them, and we will keep that. So that will be this term, parameter gradient whole square. But we will add this with the summation of all the previous gradient values, because that will be stored in the cache until the fifth iteration. The reason we store this cache value is because that will be used in the parameter updates. Remember that when we did a normal gradient descent, we just used this for the parameter update. We took a weight which is W, and then we updated the weight like this. The new weight is equal to original weight minus alpha multiplied by parameter gradient. This was the original gradient descent update. So in the original gradient descent update, we only take alpha into a multiplication of parameter gradient. So this part of the update is the same. But what is new in the ADAGrad is that we divide this by the square root of cache value plus epsilon. And remember, the cache value is the summation of the parameter gradient whole square. So let us understand the two terms of the denominator, cache and epsilon. The reason this cache term is in the denominator is that if the cache is high, which means that the parameter gradient values are historically very high, not just in the present iteration but in the past iterations also, and if that is the case, we need the step size to be smaller. So that's why we are dividing by the cache. So higher the cache, smaller is the effective step size since we are dividing by it. And if the cache is smaller, it means that the gradients are small, so the step size can be larger. And that's why we have put this cache in the denominator. So higher the cache, higher the gradient values, smaller is the effective step size. Smaller the cache, smaller the gradient values, and larger is the effective step size. And the reason we add this epsilon is that epsilon is a very small quantity. It's basically a hyperparameter which is added just to prevent the division by zero. So in the initial iteration, cache value is equal to zero. So for some reason, if the parameter gradients are all zero, we don't want to divide by zero, right? So that's why we add epsilon. So now, did you understand why did we do a parameter gradient square in the cache calculation? The reason we do a square here is that to prevent taking the square root of negative values. So when we do the parameter gradient square and then add it with epsilon, uh, it automatically means that the denominator is a positive value. So taking the square root will result in a valid answer. So we are going to update the weight values by this particular formula. So when we write it in practice, it will look like the new weights will be equal to the old weights minus alpha times the parameter gradient divided by square root of cache plus epsilon. So parameter gradient is just the gradient of the loss with respect to the parameter at the current iteration, and cache will effectively be accumulated squared gradient up till that point. So for that particular parameter, if the accumulated square gradient values are very high, we need to have a smaller effective step size, and that will be ensured since square root of cache is in the denominator. On the other hand, if the accumulated square gradients up till that point are very small, then the square root of cache will be small, and so the effective step size will be large. This is exactly what we wanted. If you look at these pieces of text over here, we wanted the higher the derivative, smaller the step size, and smaller the derivatives, larger the step size. By including this cache term in the denominator, we ensure that. When we move towards the code, let me tell you the general values for alpha and for epsilon. So alpha value is generally taken to be 1. So this is actually alpha with decay. So this will be something like here. So we are going to use a learning rate decay, and the initial step size for this ADAGrad is usually taken to be equal to 1, and then we will use a decay rate of 0.001 or 0.0001. That's the typical value which is used in practice. The epsilon value is usually used as very small, 10 raised to minus 5, 10 raised to minus 6, etc. I'll show you what these values are in the code. But for now, I just want you to intuitively understand why do we do a square root? Why do we divide by the cache? And if you think about it, we could have just replaced the cache with the current gradient whole square, right? Why do we need to take the history into account? Why are we accumulating the gradients? The reason we are accumulating the gradients is because we also want to know whether that parameter has high gradients in the past. If it has high gradients in the past, we also want to ensure that still the step sizes should be smaller. So we are not only looking at the current gradient of the parameter, we are also taking into account its past gradients as well. Before moving into the code, we can do a practical demonstration of how the cache value actually accumulates. So let's say we start, let's say there are 10 iterations and we are looking at one particular parameter which is called as W1. In the first iteration, the gradient of the loss with W1 is zero point 0.5. In the second iteration, the gradient of the loss with W1 is zero point 0.5. and this same thing continues till the 10th iteration, where the gradient of loss with respect to W1 is zero point 0.5. Now let me show you how the cache value accumulates. Initially the cache starts with 0. So the cache is denoted by capital G. G0 is 0. Then remember, to calculate the new value of cache, we add the old value of cache plus the current gradient square. So capital G1 will be G0 plus G1 whole square. Small g1 is the current gradient, which will be 0 plus zero point 0.5 square, which is 0.25. This is the first cache value. The second cache value is the previous cache value g1 plus the current gradient, which is small g2 whole square. So this will be 0.25 plus zero point 0.5 square, which is zero point 0.5. Similarly, when we reach to the 10th cache value, this will be capital G9, which is the previous cache value, plus small g10 whole square, which is the current gradient whole square, and this value will be equal to 2.5. So when we are going to do the weight update, the W1 weight update at the 10th iteration, ideally what we will be doing is we will be just doing W1 equal to W1 minus alpha into 2.5 for normal gradient descent. But now we will divide it by square root of cache value plus epsilon. So since we did 10 iterations, the cache value is 2.5. So that's why we are dividing it by 2.5. Okay, so this is how it is simply used in practice. We just accumulate the sum of the squared gradients and we divide it by the square root plus epsilon. I also want to highlight one disadvantage of the ADAGrad method because of which it did not become too popular. See, we are doing 10 iterations here, right? And the cache value has already reached 2.5. If we did 100 iterations, so if we did 100 iterations, you will see that the cache value actually reaches uh, a value of 25. If you actually do 10 raised to maybe 5 iterations, you will see that the cache value actually reaches to 5, 0, 0 and 0, 25,000. Do you see the problem which will happen if the cache value reaches 25,000? What will happen is that if we divide by 25,000, this whole part will be very, very small. So that means that the weights will not get updated at all after those many number of iterations. So after 10 raised to 5 iterations, the weights will not get updated at all. That is the main problem with ADAGrad. What's happening is in ADAGrad is that the cache value is continuously increasing, right? Because we are updating the previous, we are adding the previous gradients. So the cache value is continuously increasing, which means this denominator is continuously increasing. So if we reach the a particular stage, let's say at 1000 iterations or 10,000 iterations, where the denominator value becomes very high, the weights will not get updated at all, and so the learning will stagnate, the learning will not improve at all. This is the main disadvantage of the ADAGrad optimizer. Please keep this in mind because sometimes this question is asked in interviews as well. So one of the main disadvantage of ADAGrad is that in the cache it keeps on accumulating the sum of gradients, so the cache will keep on increasing. Now as we reach very high number of iterations, the cache value can become very large. That might make the denominator very large, so the step size effectively will become very, very small, and so the weights won't update at all. Our learning will stagnate, and I demonstrated this to you via numbers. If we have 10 iterations, the cache will be 2.5, but if we have 100,000 iterations, the cache will be 25,000. So imagine dividing by square root of 25,000, already it will be a very small, the effective learning rate, so the learning will stagnate. Okay, so now I hope you have understood the intuition behind the ADAGrad optimizer and also the mathematical equations which govern the ADAGrad optimizer. We are now going to jump right into the Python code where I'll be showing you how to implement the ADAGrad optimizer class and also running our code on a specific data set. So before jumping to the ADAGrad optimizer, let me show you the data set which we are using in our example. So this is the data set, Every point on this data set has two attributes, x1 and x2, and it belongs to either of the three classes, red, green, or blue. Our goal is to design a neural network. So our goal is to design a neural network which looks something like this, to classify correctly which color a point belongs to. So let's say we have optimized the weights and biases of the neural network, and if I give it a new data point, the neural network should tell it correctly whether it's red, green, or blue. So that's the problem which we are considering. And now let me jump towards the ADAGrad piece of code. Okay, so first we'll define the optimizer ADAGrad class. And in this class, there are different methods such as init, pre-update params, update params, and post-update params. Let me explain each of them. In the init method, this method will be automatically called when an instance of this class is created. What will happen in this method is that we will keep track of some parameters. So for example, as I told you, we will use a learning rate decay, right? So the decay parameter by default is 0. It will keep track of that parameter. It will keep track of the learning rate alpha naught. So remember, let me take you to the decay formula again. So the learning rate decay formula is this: alpha naught divided by 1 plus learning rate decay into time. So there are two parameters here, the initial step size and the learning rate decay. So by default, we start with an initial step size of 1 and a learning rate decay of 0. And in this method, we are also tracking the current learning rate. So the learning rate will be changing with time, right? According to this formula over here. So we are tracking the current learning rate here, and we are also tracking the iteration number which we are on. The reason we track the iteration number is because the learning rate depends on the iteration number. Higher the iteration number, smaller the learning rate. So these are the parameters which we are tracking. We are also tracking epsilon. This epsilon is used in the ADAGrad denominator, and I showed you that over here. So you can see we add an epsilon in the denominator, and the epsilon value is very small, 10 raised to minus 7. We usually don't change this value after defining it. Then before any parameter updates, we first update the learning rate. Remember, the learning rate is changing at each iteration according to alpha naught divided by 1 plus decay rate into the number of iteration we are on. So that's why it's important to track which iteration we are doing right now. The current learning rate will be very important because when we are going to use this formula for ADAGrad, this alpha which I'm denoting here by a green color is the current learning rate. Okay, and then the most important piece of this class is the update params method. So what will happen in this method basically is that it will first create two arrays, weight cache and bias cache. Those will all be initialized to 0 right now, and the size of this arrays will be the same as the number of weights and the number of biases, because remember that for each weight we are maintaining the cache. uh, okay, and so what we will be doing here currently is that the cache value, we will be taking the previous cache and adding the parameter gradient square, right? So that's exactly what's written here. For the weight cache, we'll take the original cache. So plus equal to means we'll take the previous cache and then add the partial derivative of loss with respect to weight whole square, which is the current gradient square. Similarly, for the bias cache, we'll retain the previous bias cache and then add the partial derivative of the loss with respect to the bias whole square. And then what we will be doing is that using these cache values, we'll be updating the weights and the biases. So the new weight is equal to the original weight minus alpha, which is the current learning rate, into the partial derivative of loss with respect to w. Up till here, it's the same as normal gradient descent, but then we divide by the square root of cache plus epsilon. This is exactly what we saw over here. Alpha into gradient divided by square root of cache plus epsilon. And when you look at the bias part, it's the same. You take the bias and you subtract alpha into gradient with respect to bias, and then you divide by the square root of bias cache plus epsilon. Note that in the whiteboard, I always mentioned about weights, but the same logic and the same discussion holds equally well for the biases as well. So this is how we'll be updating the weights and the bias in the method called update params. And then the final method here is the post update params. What will happen in the post update params is that we'll just increase the iteration count by one, because we have updated the parameters in that iteration, and then we'll move to the next iteration. Whenever we move to the next iteration, remember that the learning rate will change since we are at a different iteration, and then we'll update the weights and biases according to the similar formula which we discussed over here. So this is the optimizer class, and we'll be calling it in the neural network. So now I am going to show you how to apply the ADAGrad class in practice on a practical problem. So we are going to be looking at the spiral data set which I showed you before, where there are points who belong to either of three classes: red, green, or blue. So I'm going to take 100 samples of that data set, and this is the neural network I am going to construct. I'll have one layer initially which has two inputs, because every data point has two attributes, and 64 neurons. Then that will be having a ReLU activation. Then the output of the ReLU activation will be chained with a second layer. The second layer has 64 neurons and it has three output neurons. Those output neurons will go through the softmax activation, and then I will get either red, green, or blue classification. That's why we have three output neurons. And then we will have the categorical cross entropy loss, since this is a classification problem. Okay. Now I'm going to use the optimizer ADAGrad, and the decay rate which I'm going to use is 10 raised to minus 4. Uh, so these are the parameters. If you look over here, if we don't specify the decay rate, it would have started with 0. And I'm going to use the default alpha naught, which is 1, and epsilon as 10 raised to minus 7. So I have initiated an instance of the optimizer class over here. Then I'm going to perform 10,000 iterations of the forward pass, and I'm going to perform the backward pass as well. So first we'll do a forward pass through the first layer. The output of the first layer will go through the ReLU activation function. The output of the ReLU activation function will go through the second layer. The output of the second layer will go through softmax, and then we'll find the loss, the cross entropy loss. In this part of the code, we are just printing the accuracy, and we are printing the epoch number, the accuracy, loss, and the learning rate at each epoch. Remember, one epoch is basically one cycle through the entire data set. Of course, we'll need to do the forward backward pass, because it is here that we'll be maintaining the partial derivative of the loss with respect to the inputs, weights, and biases of every layer, which will be needed to update the weights and biases. And the update rule is specified over here. The update rule is specified like this: weights new equal to weights old minus alpha times the gradient divided by square root of cache plus or cache plus epsilon. Okay, so we'll do the backward pass. We'll start right at the end, then we'll do the backward pass, then we'll do the backward pass through the second layer. This will give us the partial derivative of the loss with respect to the inputs, weights, and biases of the second layer. Then we'll do a backward pass through the ReLU, and then finally we'll do a backward pass through the first layer. This will give us the partial derivative of the loss with respect to the inputs, weights, and bias of the first layer. Now that we have all the gradients, we can essentially call these four methods: pre-update params, update params, for both layers, layer 1 and layer 2, and then the post-update params. The reason we call the update params for both layer 1 and layer 2 is because we want to update the weights and biases in both of these layers. And the way we are updating it is based on the ADAGrad formula which we saw. And then we'll call the post update params, because we are going to track the iterations, since that will determine the current learning rate. That's it. So if you think of the code, first we create an instance of all the classes, then we call the forward pass, then we call the backward pass, and then we call the methods of the optimizer, so that we tell the code how do you update the weights and the biases. So basically, what's happening in these four lines is that every weight or bias is getting updated by its own learning rate, which is determined by the cache value which it is storing for that particular weight or bias. Now I'm going to run this piece of the code and let us actually track the epoch and the accuracy. So here we can see that around 1500 epochs the accuracy is zero point 0.7. Now the accuracy is slightly stagnating, as you can see, to zero point 0.7, but it's again going up. It's 0.86, 0.85, 0.86 again. And as you can see, now we are at around, I think, 7500 epochs and the accuracy is 0.887, and now it is not changing at all. In fact, it's only slightly increasing, and now the final accuracy is 0.893. So keep this final accuracy in mind, and I want to now compare to previous accuracies. So for the SGD with momentum, we got a accuracy of 0.953, which is definitely much higher than ADAGrad. In ADAGrad right now, when we ran the code, we got an accuracy of point uh, 893. So that's an indication that the SGD with momentum might sometimes yield better results than ADAGrad. Now let's compare with just the learning rate decay. So if we just used a learning rate decay without uh, anything, so without ADAGrad or without momentum, then we can see that the accuracy was around 0.717, which is much lower than ADAGrad. So one thing is for sure is that when we implement the ADAGrad optimizer, uh, it leads to a much higher accuracy than, let's say, we just use a learning rate decay. So what I mean by just using learning rate decay is that if we didn't have this denominator, so if we didn't have a denominator which basically gives a different step size to each parameter, the only thing we'll have is the numerator. So that's just the learning rate decay, and we get a lower accuracy in that case. So this means that adding the denominator actually helps us. So adding a individual step size or an adaptive gradient for each parameter helps us. That's number one. The second conclusion is that momentum still remains our best method. So ADAGrad gave us an accuracy of 0.83 over here, but if you look at the momentum accuracy again, we had an accuracy of 0.953. So momentum still remains the best method, and that's one of the reasons why ADAGrad is not very commonly used in practice. It is used, but ADAM is an optimizer which is preferred the most, and we'll look at ADAM in one of the subsequent lectures. Now I just want to show you a video of this exact same code optimization which we did right now, so that you can understand the training much better. So I'm going to play this video right now. Okay, here you can see that the training is proceeding right now, and I want you to look at the background. So the background color is our prediction, and these dots are the true value. So you can see it. So let me play it till the end. Now it has almost stagnated. So I'm going to stop over here. Okay, so let's look at the predictions made by this particular optimizer. First of all, let's see at this portion. So in, or let's see, in this portion the boundary is green in color, but there are three red points which are clearly misclassified. Let's look at this point. The boundary is red in color, but this point is blue, clearly misclassified. Again here the boundary is red in color, but this point is blue, so misclassified. It has a good accuracy, as you can see in the plot on the right. It has an accuracy of around zero point 0.8, which is also the same accuracy which we had obtained over here. But there are some mistakes which this ADAGrad optimizer does. So it's not the best optimizer, but it's definitely much better than just using a learning rate. So this actually brings us to this lecture on ADAGrad. In the next lecture, we are going to be looking at another optimizer called RMSProp, and then using ADAGrad and RMSProp, we'll have a lecture on the ADAM optimizer. Thank you so much, everyone, and I look forward to seeing you in the next lecture. Hello, everyone. Welcome to this lecture in the Neural Networks from Scratch series. In this lecture, we are going to learn about a new optimizer for training neural networks, and that is called as RMSprop. The full form of RMSprop is root mean square propagation. Before we dive into this lecture, I would like to give a bit of context about what we have covered in the previous lectures. So it will be even fine for learners who have not gone through the previous lectures to understand this lecture. In the previous lecture, we looked at a method called as ADAGrad, which is another optimizer, and it introduces the concept of parameters having different learning rates. So, in the previous lecture to ADAGrad, the concept which gave us the best result, or the optimizer which gave us the best result with neural networks, was using gradient descent with momentum. The main idea of momentum was that when we do the weight updates, we should also keep track of the previous weight updates so that the previous update directions can influence the current update direction. This really helped to prevent the oscillations in traditional gradient descent, which can look something like this. So, if we add a momentum to the gradient descent, the oscillations are reduced and we get a much smoother convergence to the minimum. The main reason why the oscillations are reduced is that we take into account the previous weight updates. So, in normal gradient descent, we just have the current weight equal to the previous weight minus alpha times the partial derivative of loss with respect to w. So we only take the current gradient, right? But in momentum, we also add a momentum factor multiplied by the previous weight updates. So the current weight update and the direction which we take to update the weight depends on the direction of the previous changes. That's one intuition to keep in mind. Sometimes taking the past into account really helps. Taking into account the previous changes helps a lot to prevent oscillations and to lead to a better convergence. The second point to keep in mind is that all parameters can have different learning rates. In the concept of momentum, here you can see that there is this alpha, and alpha is same essentially for all the parameters. So it's a shared learning rate which decays with time. So alpha starts off with a higher step size, and then as the time proceeds, alpha actually goes on decreasing with time, but it is still shared across all the weights of the neural network. What ADAGrad introduces is that why do all the parameters have the same learning rate? Parameters should ideally have different learning rates. So the way ADAGrad does this is that it maintains a cache, and the cache updates itself at every iteration by the parameter gradient whole square. So for every parameter, a separate cache is maintained. So if the total number of weights in the neural network are 120, for every weight we have a cache which is maintained. And what happens is that if we are at a particular iteration, the cache has accumulated all the gradient loss of the all the gradient of the loss with respect to the parameter whole square from all the previous iterations. The cache has accumulated this, and then this is used to update the weights. So the weights are not just updated by weights equal to original weights minus alpha times the parameter gradient, but we divide by a factor which is called as, or which is denoted by, square root of cache plus epsilon. What this division does is that this cache value is in the denominator, right? And the cache value is heavily dependent on the parameter gradient. So if the parameter gradient is very large, this value is in the denominator, so the effective step size will be smaller. If the parameter gradients are very small, the effective step size will be higher. So if the parameter derivatives so the parameter derivative values are inversely proportional to the effective step rate. That's the main concept introduced in ADAGrad. So the concept introduced in momentum is that the past matters and we should take into account the previous weight directions. And the main concept which is introduced in ADAGrad is that it is not just enough to have a shared step size for all the parameters. For every parameter, we should maintain a cache value which depends on the accumulated parameter gradients up till that point, and we should divide the step size by the square root of this value, so that larger uh, parameter gradients will have smaller step sizes and smaller parameter gradients will have larger step sizes. We will combine both of these ideas to understand the RMS prop. So, in the RMS prop, very similar to ADAGrad, a cache is maintained. So, in the ADAGrad, the cache was just an accumulation of all the parameter gradients, right? But in the RMS prop, we'll do something different. We will update the cache with the previous value of the cache multiplied by row. The row is also called as the cache memory decay rate, and then we will add 1 minus row into gradient square. So you can see how it is different from the ADAGrad update. In the ADAGrad update, we just keep on accumulating the prior gradients, but in the RMS prop update, the current cache is equal to row into the original cache plus 1 minus row into gradient square. So the only difference between the ADAGrad and the RMS prop is the introduction of the row, but it makes a huge difference. Also, if you remember, when we looked at the ADAGrad optimizer, and if we keep track of the cache values, you will see that the cache just keeps on accumulating the square root of gradients, right? So as we increase in the number of iterations, the cache value goes on increasing a lot. Since the cache value goes on increasing a lot, this denominator becomes very large, and the effective step size becomes very small after a certain number of iterations. So the weights don't update at all, and we have some neurons which whose weights are not updating. So these are like dead neurons which don't contribute anything to the neural network anymore. That's one of the biggest drawbacks of ADAGrad. And when we write the cache update rule like this by introducing this row parameter, which is also the cache memory decay rate, we actually solve that disadvantage of ADAGrad. I'll demonstrate to you practically how we solve this. But for now, I want to focus a bit on this formula, cache equal to row into cache plus 1 minus row into gradient square. So as you can see, due to the introduction of this row term, we are kind of giving a lot of weightage to the past cache, and we are not giving that much weightage to the current gradient. Keep in mind that the row values are typically used as zero point 0.9 when they are deployed in practical settings. So if the row value is zero point 0.9, 1 minus row will be equal to zero point 0.1. So the first understanding from this formula is that we give a lot of weightage to the past cache compared to the current gradient square. That's the learning number one. The learning number two is that in ADAGrad, we continuously added the gradients, right? But in RMS prop, we add a weighted sum of the past and the present. So in that way, it has some similarities with momentum. In momentum also we are adding the previous weight updates, right? So that also takes into account the past. Similarly, RMS prop, we add a weighted sum of the past and present. So it takes into account the past values and gives a lot more importance to them than the present values. And the update rule is the same as ADAGrad. We'll be updating the weights like alpha into parameter gradient divided by square root of cache plus epsilon. But the way the cache updates is very different than our ADAGrad. First, let's take a simple example and let's see how the cache accumulates in ADAGrad. So let's say we are looking at this parameter called W1 and we are doing 10 iterations. In each iteration, the partial derivative of loss with respect to W1 is represented as small g. So small g1 is zero point 0.5, which means in the first iteration, partial derivative of loss with respect to W1 is zero point 0.5, and this is zero point 0.5 in all 10 iterations. So in all the 10 iterations, the partial derivative of the loss with respect to the W1 is zero point 0.5. Great. Now let's see how the cache updates in ADAGrad. It starts with capital G not equal to 0. The cache always starts with 0 and the cache is denoted by capital G. So in ADAGrad, as you see, we are just going to accumulate the sum of gradients, right? So the cache at iteration number 1, which is capital G1, will be capital G0 plus small g1 whole square, which is the current gradient whole square, which is 0 plus zero point 0.5 whole square, which is 0.25. The cache at the second iteration is the cache at the first iteration plus small g2 whole square, that is zero point 0.5. Similarly, when you calculate the cache at the 10th iteration, you will get a value of 2.5. Keep this value in mind. Now I am going to show you how to calculate the cache value in the case of root mean square. We are going to use the exact same configuration. We are going to use the parameter w1 and the partial derivative of the loss with respect to W1 in all 10 iterations is 0.5. Similar to ADAGrad, even in RMSprop, the cache starts with a value of 0, but at the first iteration, the cache value is zero point 0.9, which is a row. So I'm going to use row as zero point 0.9, and let me change this to pink or a different color rather, just so that it's easy to view. So the row value is used as zero point 0.9. So the cache value at the first iteration is zero point 0.9 into G0 plus 1 minus row, which is zero point 0.1 into G1 square, which is 0 plus zero point 0.1 into zero point 0.5 square. So this gives me a value of 0.025. Similarly, the cache value at the second iteration is row times the cache value at the first iteration, which is zero point 0.9 into G1 plus 1 minus row times gradient square. So plus zero point 0.1 times small g2 whole square. And this leads to a value of 0.0475. And at the 10th iteration, the cache value is 0.226. Now compare this with the cache value of the ADAGrad at the 10th iteration. This was 2.5. Do you see what's the problem here? In ADAGrad, the cache value is becoming very large very fast, which means that if you look at the weight update formula, which is the same for ADAGrad and RMSprop, in ADAGrad, this denominator is becoming very large, which means that the effective step size is going to decay very fast. And at some point, it will become very small that the weights are not updating at all, which leads to the dead neuron problem. But RMSprop overcomes that problem. As you can see in the RMSprop, the cache accumulates slowly. In fact, the cache accumulates 10 times slower than ADAGrad in the example which we have just considered. Due to this, the denominator value will not be decreasing, or the denominator value will not be increasing as fast as it increased in ADAGrad. And that's the reason why the step size will not decay very quickly, and we will avoid the dead neuron problem. That's one of the main reasons why RMS prop is preferred over ADAGrad. It helps us prevent the dead neuron problem, and it helps accelerate the convergence. But I want you to appreciate that RMSprop uses the ideas of ADAGrad, which are the ideas of accumulating gradient and individual learning rate for each parameter, and combines it with the idea of momentum, where we give the importance to the past and also give importance to the present. In fact, in practice, the row value is used as zero point 0.9. So we give much higher importance to the past than to the present. If you look at the parameters here, there are actually three parameters, or there are four parameters. There is this alpha, and alpha is not fixed because it is decaying. So we are going to use a decay rate, something very similar to this. We are going to start with an initial step size, and we are going to decay it, which depends on the iteration number. So alpha has two variables, alpha naught and the decay rate. So those are two variables here. Then the rho is one variable and the epsilon is another variable. So we actually have four variables when we think of the RMS prop. Uh, okay, so the main advantage of RMS prop over ADAGrad is that unlike ADAGrad, the cache is not ever increasing. As a result, the learning does not stall and we don't have the dead neuron problem. Now I'm going to take you to Python code and I'm going to write down the code for what we just understood right now. Okay. So in the previous lecture, in the previous class, we looked at ADAGrad Optimizer, and in today's class, we are going to look at the RMSprop Optimizer. Okay. So now I am going to go through the RMSprop code step by step. We will also integrate it with a neural network and run a hands-on project from scratch in Python. So first we have to define a class which is called as RMS Optimizer underscore RMS prop. This class has four methods: init method, pre-update params, update params, and post-update params. Let me explain each method step by step. The init method will be called automatically once an instance of this optimizer class is created, and we are going to be tracking many things in this method. The first thing which we are going to track is the current learning rate. Remember that the current learning rate is changing with time, because we are going to use a step size decay. So we are going to use a decay which looks something like this. So the current learning rate is the initial learning rate alpha naught divided by 1 plus decay into time. And alpha naught is the learning rate which is set to be 0.001 in RMSProp, and the decay by default is set to 0. We also need to maintain the number of iterations, because as you can see here, the learning rate, the current learning rate depends on the number of iteration we are on currently. And then we are also going to track the rho and the epsilon parameter. The rho and the epsilon parameter are the foundational building blocks in the RMSprop logic. The rho is also called as the cache memory decay rate, and it will decide how much importance or how much weightage are we going to give to the past cache. And the epsilon is basically in the denominator, just so that the denominator term does not become 0. So the epsilon value is set to a very small value, 1 into 10 raised to minus 7, and the rho is set to 0.9. So these are the things which we are tracking in the init method. Then we have the pre-update params, which is called before we make the parameter updates. And this is to set the current learning rate. The parameters will be updated based on the current learning rate. So we need to set the current learning rate. So the current learning rate is alpha naught divided by 1 plus the decay into time, which are the number of iterations. That's how the current learning rate is calculated. Then we move to the update params method. This is the most important method in the RMSprop class. What we'll be doing in this method is we'll first define the cache. We'll first define the weight cache and the bias cache, and we will create an array for it. Remember that for every weight, if there are 100 weights in the neural network, for every weight we are going to track a cache, and we are going to accumulate values in the cache. So the shape of the cache matrix for the weights, or the shape of the weight cache, will be the same as the weight shape, and the shape of the bias cache will be the same as the bias shape. So that's why we are first going to initialize all of the cache values to 0. Remember, in the practical example which we took, the cache value always starts from 0. Okay, then we are going to update the cache values, and remember that to update the cache value we are going to use this formula. Cache is equal to rho into the previous cache value plus 1 minus rho into the current gradient square. So the weight cache is rho into the previous cache value, which is layer dot weight cache, plus 1 minus rho into partial derivative of loss with respect to weight the whole square. So whenever you define a layer, the backward method in that layer will always store the partial derivative of the loss with respect to the layer weights and the bias. So the layer dot d weights will give me the current partial derivative of loss with respect to weights of that layer, and the layer dot d biases will give me the current partial derivative of loss with respect to biases of that layer. So this is how I'm going to update the weight cache, and similarly this is how I'm going to update the bias cache. Remember that when we wrote on the whiteboard, I always showed you calculations for the weights, but the same thing holds for bias as well. And then what we are going to do is that we are just going to use this rule which we have defined here. The weights is equal to weights minus alpha into the gradient divided by square root of cache plus epsilon. So weights is equal to weights minus alpha into gradient divided by square root of cache plus epsilon. Similarly, bias equal to bias minus alpha multiplied by gradient, or the partial derivative of loss with respect to bias, divided by square root of bias cache plus epsilon. Remember, if this division term was not there, then it's exactly similar to the gradient descent with just a learning rate decay. This division term here makes all the difference. And then finally, we are going to call the post update params method, which will update the iteration. Remember that we need to update the iterations and keep track of it, because whichever iteration we are on currently is going to define the current learning rate. So this is the optimizer class, and now I am going to integrate it with a neural network. So first let me tell you the problem which we are going to solve. we are going to be solving a classification problem, and the data set looks something like this. This is called as a spiral data set because you can see there is a blue spiral, there is a green spiral, and there is a red spiral, right? Each data set has two attributes, on the x-axis x1 and on the y-axis y1. So each data point has two attributes, and each data point belongs to either one of the three classes: red, green, or blue. Our goal is to design a neural network so that any new data point which is given is correctly classified into red, green, or blue. And we are going to use the RMSProp Optimizer to optimize the weights and the biases of such a neural network. So let's see how the forward and the backward pass are done, and then we'll also look at the results with the RMSprop Optimizer. Okay, so first let's load the data set. So I'm going to be using the spiral data command, and I'm going to generate 100 samples of the data and three classes: red, green, and blue. So here is the neural network architecture. I'm having the first layer with two inputs because every data has two attributes. Remember, x1 on the x-axis and x2 on the y-axis. The first layer will have 64 neurons. Then I'm going to chain it with the ReLU activation function. Then I'm going to chain the second layer. The second layer has 64 neurons and it has three outputs. So here there are three outputs because we have either three values: red, green, or blue. And then we have the softmax classification and the categorical cross entropy loss. This is the forward pass. And then I'm going to define or create an instance of the optimizer RMS prop. I'm going to use the learning rate as 0.02, which is the alpha naught value in the learning rate is the alpha naught value in this decay procedure here. So in this decay procedure, the learning rate is the alpha naught value, which I'm going to start with 0.02. The decay rate, which is this decay term here, that I'm going to use as 1 into 10 raised to minus 5, and the rho value I'm going to use as 0.99, 0.999. So I'm going to give a much higher weightage to the past than the present. And remember, what is the rho value? The rho is the main essence of the RMS prop, and it's also called as the cache memory decay rate. Okay, and then we are going to run 10,000 iterations of the forward and the backward pass. So first I'm going to run the forward pass of the first layer. The output of the first layer goes as the input to the ReLU. The output of the ReLU goes as an input to the second layer, and the output of the second layer is used to calculate the soft max and then the loss towards the end. In this part of the code, we are going to be printing the epoch number, the accuracy, the loss, and the learning rate at each epoch. Remember, epoch means cycling through the data set once. So we are going to do 10,000 epochs like this. And then, of course, we are going to be doing the backward pass, because when we do the backward pass, that's when different partial derivatives of loss with respect to weights and biases are stored. So we start the backward pass by taking the partial derivative of loss with respect to the softmax inputs. Then we take the partial derivative of loss with respect to second layer weights and biases. Then we find the partial derivative of the loss with respect to ReLU inputs. And then we find the partial derivative of the loss with respect to the weights and biases of the first layer. Once we have all these gradients, then we call the four methods of the optimizer class: pre-update params, update params, and post-update params. Remember, we are going to run the update params method for both the layer 1 and layer 2. And the reason is because we want to update the weights and biases of both these layers. So that's why we call these update params in layer 1 and layer 2. And then we are calling the post update params. After the parameters are updated, then we just increase the iteration count to 1 by 1 and then repeat this process again. So just to summarize, first we define the neural network architecture. We define or create an instance of the optimizer class where we give in the learning rate, the decay rate, and the rho as the parameters. And then we run 10,000 iterations of the forward and backward pass. And after each iteration, we are going to update the params, and then we are going to update the iteration count. Now let me run this piece of the code and let us visualize the results in terms of loss. So I'm running this piece of code, and as you can see, the loss is decreasing steadily. Currently, the accuracy is around 7.74, and as you can see, the accuracy is also increasing a bit. And you can see that we are right now at around 6000 iterations or 6000 epochs, and the accuracy has reached 0.83. So now we are at around 8000, 9000 epochs, and the accuracy has reached 0.863. So now we are at 10,000 epochs, and the accuracy has reached 0.853, and the loss has reached 0.362. So remember, sometimes the outputs may also depend on the initialization. So let me run this again in order to find the accuracy and the loss, in a hope that maybe I'll get a better accuracy this time. I may also get a worse accuracy. So let's see. I've run how many iterations? I've run around 6000 iterations, and as you can see here, the accuracy is much lower than what we were getting in the previous. Here we are getting it to 0.597. Now let me run it again. This is just to show you that the initialization of the neural network has a big impact on the accuracy. So I think this would be the best of the iterations, because here you can see that I'm reaching accuracies of around 0.85, 0.86, and at the last iteration I'm even reached accuracy of 0.87 and 0.88. So keep this value in mind, and let's compare the accuracy of the ADAGrad. So when we reach the ADAGrad, here also we got similar accuracies as the RMSprop right now. So this clearly shows that in all instances, RMSprop is not better than ADAGrad. Only when the number of iterations are huge, let's say, that's when the ADAGrad learning rate starts to stagnate, and that's when ADAGrad performance becomes worse. But as we can see in this example, the ADAGrad accuracy was around 0.88, and here also we got an accuracy of around 0.88. So the final accuracies of both these models are similar in this case, but you will notice that as the data set becomes more complex and as the iterations go to 1 million or more than that, then RMSprop actually starts to perform better than ADAGrad. So RMSprop is generally preferred than ADAGrad, but in the example which we have chosen right now, RMSprop and ADAGrad are performing equally. Now let us actually compare to the case where we just used a learning decay without using RMSprop. So if we just use learning decay, let's see the accuracy which we get. If we just use learning decay, the accuracy which we get is 0.717, which is much lesser than the ADAGrad, the RMSprop accuracy of 0.88. So definitely the RMSprop updates which we have implemented and which I have mentioned over here, definitely they are much better than just using a learning rate decay. And when I say just learning rate decay, I mean if we just had a numerator here and did not have anything in the denominator, we would have got the accuracy as 0.717. But since we added the uh, RMSprop changes or updates in the denominator, we have got to an accuracy of 0.88. So remember, now you have three good optimizers to work with. First is SGD, stochastic gradient or gradient descent with momentum. And I want to just mention here that the gradient descent with momentum is still our best optimizer so far, because if you look at the accuracy of the gradient descent with momentum, we had got an accuracy of 0.93. So gradient descent with momentum is still the best accuracy, but now I have introduced two additional optimizers, ADAGrad and RMSprop in this lecture, and both lead to an accuracy of 0.88. More than the accuracy, I want you to focus on the intuition of ADAGrad. The main intuition behind ADAGrad is that it's like a accumulation of two concepts. First concept is from the RMSprop is an accumulation of two concepts. The first concept is from ADAGrad, and this main concept is each parameter should have different learning rates. And second concept is from momentum, where we give a lot of importance to the past values as compared to, let's say, the present values. So RMSprop generally has an advantage over ADAGrad, that if the number of iterations become very very high, then the ADAGrad learning rate starts to stagnate. But this stagnation problem is not there in RMSprop. As a result, the learning does not stop. in RMSprop, or the learning does not stall in RMSprop. I want to now just show you a video of this optimization which we have performed in code. So let me run this video. So as you can see in this video here, the boundaries, I want you to focus on the boundaries. The boundaries are actually an indication of how well we are performing with the data set. And as you can see, the boundaries have also started to look like spirals, right? Which means we are generally doing well, but there might be some misclassifications. So for example, if you look at the red point here, the boundary is blue, which means our prediction is blue, but the actual value for this red point is clearly red. So this is a mistake. Similarly, there are small mistakes which you will notice, such as for example, this blue point is in a red boundary. So I can see that we are getting to a spiral shape, which is amazing, and which means that the RMS prop is working. But it's still not the best accuracy as what we had got with the SGD, or the gradient descent with momentum. This actually brings us to the end of this lecture on RMS prop. I wanted to cover it in a lot of detail. Um, in the next lecture, we are going to look at one of the most widely used modern neural network optimizers, and that's ADAM. But to really understand ADAM, it was very important to first explain ADAGrad in the previous lecture, and now explain RMSprop in this lecture. Thank you so much, everyone, and I look forward to seeing you in the next lecture. Hello, everyone. Welcome to this lecture in the Neural Networks from Scratch series. Today, I am very excited because today we are going to learn about an optimizer which is used in most modern machine learning frameworks. If you are working in an industry, or if you are working on a research project, and if you have designed a neural network to solve any problem, the default optimizer which all engineers generally start with is the ADAM optimizer. In the previous lectures, we have looked at normal gradient descent, we have looked at momentum, and we have also looked at ADAGrad and RMSprop. If you have not seen these lectures, I highly encourage you to go through them so that you will appreciate this lecture even more. I deliberately have constructed those previous lectures so that when we come to ADAM, your concepts will be clear, because we will be using all of those building blocks while constructing the ADAM optimizer. If you have not seen the previous lectures, no problem at all. I've designed this lecture so that I'll go from the start to explain each and every step. My name is Dr. Raj Dandekar, and I have a PhD in machine learning from Massachusetts Institute of Technology. I graduated with my PhD in 2022, and before that, I graduated with a BTech in mechanical engineering from IIT Madras. So, let's get started. ADAM Optimizer was constructed in steps. So, a number of advances happened before researchers eventually reached the ADAM Optimizer. And it's very useful as we learn machine learning to go through these advances sequentially. First came gradient descent. When there was a neural network, people realized that to optimize the weights and biases of the neural network, one of the best strategies is to move in the direction of the steepest descent so that we reach the minima of the loss function. And the direction of the steepest descent is given by negative of the gradient. Negative of the gradient. That's why people formulated the gradient descent procedure. So, whatever weights and biases which we have, you start with some random weight or bias, and then you keep on updating the weights or bias by moving in the direction of the steepest descent. That's why you subtract a learning rate multiplied by the partial derivative of the loss with respect to the weight or with respect to the bias. You keep on doing this iterative procedure for a large number of iterations, and then the hope is that you will eventually reach the minima, or you will minimize the loss function, and the neural network will be optimized. So here you can see that there is a fixed step size. So whichever weight you are looking for, whichever bias you are looking for, all of the weights and biases have a fixed step size which is shared among all of them. That is the first feature of normal gradient descent. So this is the first feature. The second feature of the normal gradient descent is that to update the weights and the biases, only the current value of the gradient is used. So for example, if you have reached the 50th iteration and you want to find the weight at the 51st iteration, then you take the weight at the 50th iteration and then you subtract alpha times the partial derivative of loss with respect to w at that current iteration at the 51st iteration, and that is how you find the current value of the weights. So here you can see that only current gradient value is used and we do not give any importance to the past gradient values. So for example, you might be asking, what about the partial derivative of loss with respect to the weight for the first iteration, second iteration, 49th iteration? Don't they matter at all? And in normal gradient descent, the answer is no, they don't matter in normal gradient descent. People soon realize that normal gradient descent has a huge number of disadvantages. The first disadvantage is that we get stuck in a local minima. So let's say if the loss function landscape looks something like this, we there is a high tendency for normal gradient descent to get stuck in local minimas like this, and it's very difficult to discover the global minima. That's one of the biggest drawbacks of using normal gradient descent, and that's due to several reasons which people try to fix slowly. The first reason is the fixed step size and trying to make it more adaptive or more dynamic. The second reason, which is more predominant, is that why do we only use the current gradient value for updating the weights? Why don't we use the past gradient values also? The past has a lot to teach us, so why don't we use it? That eventually led to momentum. The main idea of momentum in gradient descent is that the past gradients also matter. We definitely need to give importance to the past gradients. What this does is that if you give importance to the past gradients, oscillations reduce and we converge to the minima much faster. So, momentum is used to accelerate gradient descent. One way to think about this is that, let's say if the loss function landscape is something like this, and we start from here, right, and we want to reach the local minima, which let's say is here. Now ideally we should go in this kind of a manner, right, this kind of a straight kind of a line to the minima. But what happens is that if we use normal gradient descent, we will keep on moving in the direction of the negative gradient at that point, so that will lead to the zigzag oscillations like these. If you use momentum at a particular iteration for a particular weight, all the past weights are also given precedence. And when you give precedence to the past weights, the directions in left and the directions in right cancel each other out. And the only direction which survives is the direction in the vertically downward. So if we use momentum, it's more likely that we get this streamlined descent towards the minima and we reduce the oscillations. The way that this is represented in mathematical formula is that the new weight is the old weight minus step size multiplied by the partial derivative of loss with respect to w. This is the same as for normal gradient descent. The only difference is that we add this factor here. So we add a momentum factor multiplied by the previous weight updates. So here you can see in this term, the previous weights are also given a lot of importance, or rather I should say the previous gradient values are also given a lot of importance. The current gradient is not the only one which is used. This formula is also, this same thing which I have written over here is also sometimes represented as this formula. The current weight is equal to the previous weight minus the learning rate multiplied by beta, which is the momentum factor and which controls how much weight is given to the past, multiplied by the current momentum value plus 1 minus beta times partial derivative of loss with respect to w. This is the current gradient. So it's this term which actually adds the weightage to the past values or the past values of the gradient. Um, to those who are familiar with more advanced mathematics, this term in the bracket is also sometimes called as the moving average. To those who are not familiar, it's completely fine. The way this term is represented, it actually means that we are giving a lot of importance to the past or the previous weight updates. That's the whole concept behind momentum, and it really does accelerate the convergence in a gradient descent by a huge factor. And it's routinely used in gradient descent. So momentum with gradient descent is much better than normal gradient descent. One problem with this method is that here again the step size is common and it's shared across all the parameters, right? But people soon started to wonder that why is the step size same for all the weights? So let's say if the loss function landscape looked something like this, right? Uh, and it's given by this function that w1 square by 100 plus w2 square. Let's say this is my loss function. Now you can see that even small changes in W1 will not lead to too much changes in the loss because there is a division of 100 here. But small changes in W2 will be now 100 times more powerful because it does not have the division factor. So shouldn't this mean that we should take larger step sizes for W1 and smaller step sizes for W2? Shouldn't we have adaptive gradients? The main idea of adaptive gradients is that smaller the gradient, higher is the step size. So for W1, the gradient is small because small changes in W1 lead to no changes in loss. So we should use higher step size for W1. Otherwise, W1 won't get updated at all. And for W2, the gradient is large. So we should use a smaller step size. So then people started thinking that this makes sense because if we don't use adaptive step sizes, then W1 will almost stagnate and not contribute anything, and only W2 will keep on changing in the iterations. So all the neurons which are associated with W1 will essentially become dead, and that would lead to the dead neuron problem where some neurons won't contribute at all. This is not good. So that led to the idea of adaptive gradients, where the main idea was that every weight should have a different step size, or an adaptive gradient rather, um, so that the step size effectively depends on the gradient value for that parameter. If the gradient value of the parameter is large, the step size will be small. If the gradient value of the parameter is small, the step size will be large. This led to the RMSProp method, where the update rule is given by this: the current weight is the old weight minus the learning rate multiplied by the partial derivative of loss with respect to W. Now, when I say learning rate, you can consider this whole thing as the learning rate. And you will see that if the denominator is not there, this just it's normal gradient descent. But it's the denominator which makes the learning rate adaptive. Let's see how. The denominator is given by this formula: beta 2 multiplied by the cache value. So cache is equal to beta 2 multiplied by the cache plus 1 minus beta 2 into gradient square. So if you look at this formula here, over here we gave importance to the past gradients, right, while computing the momentum. Here you can see that it's a very similar formula, but we are giving importance to gradient square. And since this cache value comes in the denominator, higher the gradient, higher will this value be, and smaller will the effective step size. Smaller the gradient, higher will the cache value be, and smaller will be the. So higher the gradient, higher the cache value, smaller the step size. Smaller the gradient, smaller the cache value, and higher the step size. Now, the way the cache value is calculated is that we definitely give importance to the past gradient square also. So we don't just keep on accumulating the current gradient, we give importance to the past gradient square also. So whenever something like this is introduced where beta is there and 1 minus beta is there, it means that we are giving importance to the past. And instead of gradient, here we have gradient square. And instead of the beta 1 parameter here, we have the beta 2 parameter here. This beta 2 parameter is called as the cache memory decay rate, and it controls how much importance do we give to gradient square. So if we are at a particular parameter, okay, and we are wanting to update the parameter value at a current iteration, we first take into account all the gradient square values for that parameter. So we find partial derivative of loss with respect to the parameter whole square for all the previous values, and through that we compute the cache value. So if beta 2 value is very high, a lot of importance will be given to the previous gradient square parameters. And the reason it's gradient square is because we are using a square root here. So we are kind of effectively dividing by only the gradient. And the reason the epsilon parameter is added here is to prevent the denominator from becoming 0. So this thing which I have shown in the orange bracket here, it introduces the adaptive learning rate for each parameter. And that's the main idea of optimizers like RMSProp, or even optimizers like ADAGrad or ADA So here we can see that this is a bit different than momentum, because we do not take into account the past gradients here. So here you see the current, only the current partial derivative of loss with respect to W is used. But we do take into account the past gradient square for finding these adaptive step sizes. So you should now appreciate the difference between momentum and RMS prop. In momentum, the past gradients matter, and they matter for finding the current gradient term. In RMSprop, the past gradient square matters, and they matter for finding the adaptive or effective step size. But in the current gradient, the only the current gradient is used, partial derivative of loss with respect to W. That's the difference between RMSprop and momentum. But both momentum and RMSprop are significant improvements to the normal gradient descent. The main idea behind the ADAM optimizer is that what if we combine momentum with adaptive learning rates? Let me reframe this differently. Let's look at this particular formula here, right? We are using adaptive learning rates, but here we are only looking at the current gradient value, right? So the main idea of ADAM is that what if this term, which is the current, which is the partial derivative of loss with respect to weight in the current iteration, what if this term is replaced by this term which was used in the momentum? So what if this term was replaced with the momentum term? So instead of just using the current gradients, what if we replace this with the current momentum, so that we take into account all the past gradients into consideration? This will use the advantages of the momentum method, as well as it will use the advantages of the adaptive step sizes as introduced in the RMS prop. So it will kind of be the best of both worlds for us. And that is the main idea behind the Adam optimizer. So what the Adam optimizer says is that, the why don't we do this, why don't we say that the present weight is the old weight minus the learning rate multiplied by the momentum term. So instead of using the partial derivative of loss with respect to W, we use the momentum term here, as you can see, which gives importance to the past weights also, past gradients also. And then we divide by the square root of cash plus epsilon, which was exactly similar to what we did in RMS prop. Uh, so let me call this numerator term as momentum term, and let me call this cash over here as cash term. In the Adam optimizer, there is one small addition which is done. So what is done here is that sometimes this momentum term can start out with a very small value, so it might lead to the cold start problem for us, right? So we don't want that. We want the initial weights to make quick updates so that we explore the entire loss landscape. So for example, if the loss landscape looks like this, okay, and the initial weight updates are very small, we'll just keep getting stuck in this part. But there are a lot of other areas in the loss landscape to explore. So we want the initial weight updates to be quick so that we explore these other loss landscape also, other parts of the loss landscape also. So what we'll be doing is that we'll be dividing the momentum term by a correction factor called 1 minus beta 1 raised to t, and we'll be dividing the cash term by a correction factor called 1 minus beta 2 raised to t. Why this term? Because see, if t is very small, first you can see if t is very large, remember beta 1 is less than 1, so let's say beta 1 is 0.9. So if t is very large, it, let's say 0.9 raised to 50, this will almost be close to 0. So for higher iterations, it's like dividing. So this term will be 0. So it's like dividing by 1. So it will make no impact at all. But for lower iterations, let's say t is equal to 1, then this division term or this correction term will be 0.9 raised to 1, which is zero point 0.9. So 1 minus zero point 0.9 will be, so this term will be zero point 0.9, and 1 minus zero point 0.9 will be zero point 0.1. So we'll be dividing the momentum term by zero point 0.1. So which will increase it by 10 times, right? Which will make sure that the weights are getting updated. Similarly, for the cache term, if beta 2 is equal to point, if beta 2 is equal to 0.9, uh, if t is very high, this term will be approximately 0. So it will be like dividing by 1 and no changes at all if we are at higher number of iterations. But if we are at the iteration number 1, then this will again be 0.9 raised to 1. So it will be 1 minus zero point 0.9, which will again be zero point 0.1. So then it will be dividing the cache term by zero point 0.1, which is multiplying it by 10 times. Again, that will ensure that the weight updates are happening in the initial iterations. Combining these two things, we ultimately get the final formula for the ADAM optimizer weight updates. So W is equal to W minus alpha into momentum term divided by 1 minus beta 1 raised to t. This is the correction factor, divided by square root of cache term divided by 1 minus beta 2 raised to t. This is the correction term, plus epsilon. And epsilon is added just to make sure that the denominator does not become 0. That's it. If you look at the parameters in the ADAM optimizer, there are generally two parameters, beta 1 and beta 2. Remember the origins of beta 1. Beta 1 controls the momentum term. So it defines how much importance is given to the past gradients in the gradient update. Whereas if you look at the cache term has beta 2, and beta 2 is called cache memory decay rate, and it controls how much importance is given to gradient square. So how much importance do we need to give to the past to adapt the learning rates? Generally, in practice, beta 1 is taken to be around zero point 0.9 and beta 2 is taken to be around 0.999. Imagine this, beta 2 is 0.999, which means that when we calculate the cache term, we give tremendous amount of importance to the past gradients. So let's say if I am at a current iteration of a parameter and its past gradients are very high, even if its current gradient is low, I am going to use a small step size because I will give so much importance to the past gradients. So this is the ADAM optimizer, and as you can see, it builds upon two key concepts. The first key concept is that of momentum, and the second key concept is that of adaptive learning rate. And what is the adaptive learning rate? It's this term which I am right now marking in the orange color. You can think of this as the effective learning rate, whereas this term is the partial derivative or is the gradient term. So instead of just using the current gradient, we also give importance to the past. And that's the reason the ADAM optimizer has two parameters, beta 1 and beta 2. That's it. This is the simple explanation of ADAM optimizer and the origins of the ADAM optimizer in the first place. I hope you have understood up till this part and how we reached the ADAM optimizer, starting first from the gradient descent, then moving to the momentum, then moving to RMSProp, and then finally using all those building blocks to construct the ADAM optimizer. Now, in part 2 of this lecture, I want to actually take you through the practical demonstration of this. But before that, the first one thing I would like to clarify is that when I use alpha here, this alpha itself is not fixed, but it will be decaying with time. So generally, the decay is prescribed by alpha naught divided by 1. So let me show this rather than writing it again. Let me show it over here. So generally, the alpha is given by alpha naught divided by 1 plus decay into time, where this is the learning rate decay. So even the alpha, when I say it's not fixed, it's decreasing with time to make sure that the initial learning rates are high. All of this we are doing to make sure we don't have the cold start problem and the weights are not getting stagnated at the start. Okay, so in the part 2 of this lecture, I am going to implement the ADAM optimizer completely in Python, and I'm going to show you step by step how to code the ADAM optimizer and how to solve an entire neural network using the ADAM optimizer. So let us implement this in code. First, let me explain the problem statement to you. This is the data set which we have. If you look at the data set, every data point has two attributes, x1, or two features, x1 and x2. And if you look at any particular data point, let's say this, it belongs to either one of the three classes. It belongs to R or G or B. The goal for us is to train a neural network so that any new point, let's say if this new point is given to us, Based on its values x1 and x2, we should be able to correctly classify whether it belongs to the red class, whether it belongs to the green class, or whether it belongs to the blue class. That's the problem which we have to solve. And this is a classification problem. So let's first see how the neural network architecture will look like. This is the neural network architecture which we are going to use, and this is the same one I'll be coding out today. So first, the data point has two input features, x1 and x2, and they'll be going through the first layer. So the first layer in this neural network has, let's say, 64 neurons, and then every neuron has a ReLU activation function connected to the output. After the output goes through the ReLU, it's passed to the second layer. In the second layer, there are just three neurons, and the output of these neurons is passed through the softmax. And then we'll get some output. For each input, we'll have three different outputs. So let's say if for the current x1, x2, the output is zero point 0.9, zero point 0.1, and 0. This clearly says that there is 90% probability that this point belongs to red class, and 10% probability that this point belongs to green class. And based on these values, then we'll calculate the loss based on the actual data. So this is how we'll train the neural network to make the correct classification between red, green, or blue. And we'll be using the ADAM optimizer for it. So let me jump into code to show you how exactly this is done. So before we actually integrate the ADAM optimizer with the forward and backward pass of the neural network, we first need to define a class, and that class is called as optimizer ADAM. This class will have four methods. It will have the init method, the pre-update params, the update params, and then finally the post-update params. Let me explain each method step by step. So when we create an instance of the optimizer class, it will by default call this init method. Now we are keeping track of many things in this init method. So if you have understood this this formula, you will really understand what all different parameters I have. First, let me start from these parameters: beta 1, beta 2, and epsilon. Okay. So beta 1 is by default set to zero point 0.9, and remember, beta 1 is the momentum, how much momentum rate or how much importance is given to the past gradients. Beta 2 is the cache decay memory rate, and it governs how much importance is given to the gradient square in the adaptive learning rate. So by default, beta 1 is set to zero point 0.9 and beta 2 is set to 0.999. So these are the two parameters we track. We also track epsilon. Remember, epsilon is added to the denominator to make sure denominator is not 0, and it is typically a very small value, 1 into 10 raised to minus 7. Other parameters which we track all correspond to this alpha. Remember, this alpha term which is here is not constant, but we are going to use the adaptive learning rate, or rather the learning rate decay. So I'm just going to go to that part where, yes, so the alpha, for alpha we are going to be using the learning rate decay. So alpha is alpha naught divided by 1 plus decay into time, right? So we need to keep track of three things. We need to keep track of initial step size, the decay rate, and the iteration number, right? And these three things which we need to keep track of have been mentioned over here. So first is the initial learning rate, which is by default set to 0.01. Second is the decay rate, which is by default set to 0. And third, we also need to keep track of the number of iterations, because as you can see here, the learning rate also depends on the number of iterations, which is mentioned by t over here. That's the iteration number. So all of this we are keeping track in the init method. Then we come to pre-update params. So before we update the parameter values, we need to calculate this alpha, which is alpha naught divided by 1 plus decay into time. So this alpha is the one which has been mentioned over here, this alpha. So first we need to calculate this alpha, and that has been calculated in this pre-update params function, where the current learning rate, as I mentioned, is alpha divided by 1 plus decay into time. Then comes the most important method, where we are actually going to update the parameters. Okay, now I want you to focus on two things. First, in the code, or in the whiteboard rather, I always talked about weights, right? But the same thing will be done for the biases of the neural network as well. So in the update params method, you will see that there is the update rule for weights as well as biases. So I'm just going to focus on the weights here, and you can apply the same learning or the same logic to biases also. So there are two things which we need to keep track of. There is this numerator, which is the momentum term, and there is the denominator, which is the cache term, right? So for every weight and for every bias, we will have a momentum term in the numerator, and we will have a cache term in the denominator. So first we create empty matrices. So for the momentum term, it will have the same dimensions as the weights of the neural network, because every weight will have a momentum term associated with it. Similarly, the cache value has the same size as the number of weights in the neural network, because for every weight we are maintaining a cache. Remember, every weight has a different step size, right? So for every weight we are maintaining a cache value, and the same thing happens for bias also. Then what we are going to do is we are going to update the momentums. So if you look at the momentum which is mentioned over here, let's look at the momentum term. It's beta 1 into the previous momentum plus 1 minus beta 1 into the current gradient. So remember this formula, it's beta 1 into the previous momentums plus 1 minus beta into current gradients. So remember, layer, when we initiate a class of the layer, it has the backward method in it. So we are automatically storing the partial derivative of loss with respect to the weights and biases of that layer. Similarly, for bias, we do beta 1 into the past bias plus 1 minus beta 1 into the partial derivative of loss with respect to bias, which is the current gradient. And then we are going to employ the correction term. So remember that the momentum term is going to be divided by this 1 minus beta 1 raised to t. So in this part of the code, we are implementing the correction term. We take the momentum term and we divide by 1 minus beta 1 raised to t. For practical purposes, we have added 1 in the denominator so that the iterations don't start from 0 and we don't have a division by 0 over here. Or rather, we don't have starting from a very large value. I think that's why a plus 1 is added. So remember, this is beta 1 raised to t plus 1, right? It's not beta 1 multiplied by t, but it's 1 minus beta 1 raised to t plus 1. You can also do it just with t, but I've seen that in all the codes it's always the plus 1 is added. I think it helps to give a better start to the initial weights and the biases. The similar thing is done for the bias correction term as well. And then finally, we look at the cache. So remember, the formula for the cache is that beta 2 into the previous cache plus 1 minus beta 2 into the current gradient square, right? So the weight cache is beta 2 into the previous cache plus 1 minus beta 2 into the current gradient square. Similarly, the bias cache is beta 2 into the prior bias cache plus 1 minus beta 2 into the current gradient of the bias whole square. Remember, when two star operators are put together in Python, it's actually the exponent or raised to. Then we get the corrected cache. So similar to the way we corrected the momentum in the numerator, in the denominator we will also need to correct the cache term, or we'll need to divide it by 1 minus beta 2 raised to t. So what we'll be doing is that for the weight cache and the bias cache, we'll be dividing the denominator by 1 minus beta 2 raised to t plus 1. Again, the plus 1 is added here, similar to for the momentum. For the bias also, we take the bias cache and divide by 1 minus beta 2 raised to t plus 1. Then that's it. Once we have calculated the numerator term, which is the modified momentum, and the denominator term, all we need to do is update the weights. So the new weight is the past weight minus alpha times the momentum divided by square root of cache plus epsilon. That's exactly what's done here. Weights, the current weights are the previous weights minus alpha times the corrected momentum divided by square root of the corrected cache plus epsilon. Similarly, for the biases, the current bias is equal to the past bias minus alpha times the momentum in the bias corrected divided by square root of bias cache corrected plus epsilon. So this is how then the weights and biases of every single layer of the neural network are updated according to the ADAM optimizer. And finally, it's very important to call the post update params. After we update the parameters, we need to increase the iterations, because remember that the next iteration step size depends on the number of iterations. Alpha is equal to alpha naught divided by 1 plus decay into t. So we definitely need to keep track on the number of iterations which we are on currently. And that's why we need to call the post update params. So now this is the ADAM optimizer class, and I'm just going to run it. So okay, this has been run, and now I am going to implement this class on the neural network. Please remember the neural network data set which we have. So this is called as spiral data. And please also remember the architecture. We are going to be using 64 neurons in the first layer, then ReLU, then 3 neurons in the output, then softmax, then the categorical cross entropy loss. So first we create the data set. We are using spiral data set here with 100 samples, and it has three classes. It can belong to red, green or blue. Then we create the first layer. The first layer has two inputs and 64 neurons. We chain it with the ReLU activation function. Then we create the second layer, which has three neurons. Then we chain it with the softmax and the categorical cross entropy loss. This is exactly following the architecture which we have drawn on the whiteboard over here. Once we have written up till this part, we have to specify the optimizer. In the previous lectures, we have tested with SGD, ADAGrad and RMSProp. In today's lecture, we are going to be using ADAM, and the learning rate, which is the alpha naught, is 0.02, and the decay rate we are going to use is 10 raised to minus 5. All other parameters have already been predefined here, such as epsilon, beta, which is beta 1, which is zero point 0.9, and beta 2, which is 0.999. Great. Then we come to the forward pass and the backward pass. So we'll be doing 10,000 iterations of the forward pass and the backward pass. Remember that in each forward pass, we calculate the output of all layers of the neural network. In the backward pass, we find the partial derivative of the loss with respect to the weights, the inputs, and the biases of the neural network. And then we'll update the weights and biases of the neural network based on the optimizer, ADAM optimizer. So the first thing what we do is forward pass through the first layer, which is the forward pass through this first layer. So let me actually mark it with a different color. The first thing what we'll be doing is taking the forward pass through this layer, then going through the ReLU. So we take the forward pass through the first layer. The output of the first layer is fed as the input to the ReLU activation. Then we do the forward pass through the ReLU activation. The output of the ReLU is fed as an input to the next layer, which is the second layer. And then we calculate the softmax and the categorical cross entropy loss. So all these four statements up till here are the forward pass. In this part of the code, we are just printing out the epoch number, the accuracy, the loss at every epoch. And remember, the learning rate is adapting. So the learning rate is changing with each epoch. So that also we are printing it out. One epoch is just going through the data set entirely once. So keep that in mind. And then we will be running the backward pass. So first we will find the partial derivative of the loss with respect to the softmax input. Then we'll find the partial derivative of the loss with respect to the weights and biases of the second layer. Then we will find the partial derivative of the loss with respect to ReLU input. And finally, we'll find the partial derivative of the loss with respect to the weights and biases of the first layer. Once we have found all the partial derivatives of the loss, we are ready to call the different optimizer methods which we have defined over here. So first we are going to call the pre-update params, which will make sure that the learning rate is updated. Then we are going to call the update params, which will make sure that the weights and biases of every layer are updated according to the current partial derivatives of the loss with respect to those weights and biases. And then we will call post update params just to increase the iteration number and to keep track of the iterations. So we call pre-update params, then we call update params for the layer 1, and we call update params for layer 2, because the parameters of both these layers need to be updated. And then we call the post update params to make sure that then we call post update params to make sure that the iteration number is updated so that the learning rate in the next iteration can be adapted accordingly. So this is how the entire forward and backward pass code is written with the ADAM Optimizer class, and I'm going to run this code now to see the outputs. So let's see the outputs here. We can see that we are running 10,000 epochs. So you can see 10,000 epochs has been run, and let's see the final accuracy. It's 0.957, and the loss is 0.099. So let me note down this accuracy here, which is for the ADAM optimizer, we got the final accuracy as 0.957, right? Which is amazing. And here you can see that the loss has decreased to 0.099. If you have followed the previous lectures, you will see that this is the best accuracy which we have got so far. But now we can test out different accuracies, right? So first I am going to test out the accuracy with just the let's say if I test it out with RMSprop. So if I test it out with RMSprop and then just run it. So remember that RMSprop just uses the cache value and it does not take into account the momentum term in the in the numerator. And the RMS prop is now running, and right now I'm at around 3000 epochs, and here you can see that the accuracy is still 0.63. Let's see how much the accuracy is when we reach around 10,000 epochs. So now I'm at epoch number 7600. Okay, finally I'm at 9000 epochs, and now you can see that 10,000 epochs have been completed and the accuracy is 0.717. So for RMS prop, the accuracy is 0.717, which is nowhere compared to the ADAM optimizer accuracy which we obtained. Now let us try to see the accuracy for just the stochastic gradient descent with momentum. So this is with momentum, but we are not using the adaptive step sizes like which are used in RMS prop and ADAM. So let's run this right now. Okay, so as you can see, I'm running the SGD or the gradient descent with momentum rather, which just uses the momentum term in the in the numerator, but it does not use the cache term in the denominator. So here you can see that we are getting a better accuracy, which is good, and the accuracy will reach to around zero point 0.9, I think. So we are at around 10,000 iterations, and the accuracy is 0.873. So I'll just write just using the momentum, the accuracy is 0.873. Sometimes when you run different iterations, you will see that the momentum accuracy is as high as Adam. So momentum is good, but for all other problems of neural networks and machine learning, the Adam optimizer is the best optimizer to get started with, because it takes into account the momentum, plus it takes into account the adaptive learning rate or the cache term which is used in RMS prop. This is amazing, right? Now I just want to take you through some videos to show you the difference between the Adam optimizer, convergence, and the other optimizers. So first let me just show you, if we just use a decaying learning rate, and here we are not even using momentum, we are not even using the cache term in the denominator. This is just a decaying learning rate. So here you can see that the iterations will start now. Okay, here you can see that the iterations have started, and if you see the background colors, they are the predictions. They should ideally match the true data colors which we have. uh, so now if you can see, this is the final prediction if we just use a decaying learning rate without momentum or without the RMS prop. Here you can see it's pretty bad, right, with respect to prediction, because if you see these points over here, our prediction, which is the blue background, that's our prediction, but these two are green, so they are misclassified. If you take these points here, they are in a green background, so these red points are misclassified. So it's not very good. Now let's look at the RMS prop. The RMS prop optimizer does not use momentum, but it uses the cache term in the denominator, and it does a slightly better job. So here you can see that it's kind of looking like a spiral now. It's not exactly looking like a spiral, the outside color. It's definitely doing a better job than just using the decay rate without momentum or without the cache term in the denominator. So here also you can see that there are a number of misclassifications. These green points over here are misclassified as blue. Then this blue point here is misclassified as red, etc. So it's not the best. Now let's look at Adam. So I'm going to be running the Adam optimizer now. So here you can see right from the start, the Adam optimizer leads to amazing results. Here you can see that the if you look at the backgrounds, they look like spirals. So this is the final result given by the ADAM optimizer, and you can see that almost all points have been classified correctly. There are very few misclassified points. The border colors which we have look like spirals which match the colors of the data points. This is brilliant, right? This clearly shows that the ADAM optimizer is probably the most robust optimizers among the different ones which we have tested. Okay, so thank you so much everyone for attending this lecture, or for listening to this lecture. I tried to explain ADAM right from the basics, and I tried to motivate the concept of ADAM through first showing you momentum, then showing you gradient descent, then showing you the cache term, and then showing you how all of these three tools. So first we have the normal gradient descent, then we have momentum, then we have the cache term, and then showing you how all of these contribute together to lead to the ADAM optimizer. So the ADAM is just a culmination of these building blocks which people had worked on previously, but it turns out to be the best and most robust optimizers which is used in many machine learning settings. Remember that the ADAM has two parameters which are most important: the beta one, generally taken to be around zero point 0.9, which is the momentum factor, and the beta 2, which is the cache memory decay rate, or the adaptive, or the rate which controls how much importance is given to the gradient square or the past gradient square values to make the adaptive step sizes. And then we looked at the ADAM optimizer in code. We saw how the ADAM optimizer class was created and how it was integrated with the forward pass and the backward pass. I hope you are deriving a lot of value from these lectures. When I was taught ADAM for the first time, I did not really understand it at all. But I realized that you need to break it down into different small concepts, and when you put them all together, it's quite easy to understand. I really encourage you to write all of the steps which I am describing here, and to also replicate the codes which I am providing. Thank you so much, everyone, and I'll see you in the next lecture.